The reef at first glance appears chaotic, a riot of color and movement where hundreds of species weave through coral spires as if following no plan at all. Yet beneath that visual noise exists a precise logic shaped by hunger, risk, and the unforgiving mathematics of survival. Massive groupers patrol this environment with an authority earned not through speed, but through patience, bulk, and an uncanny understanding of how space can be weaponized. Their bodies, thick and muscular, move with deliberate restraint, because in a coral reef, brute force alone is inefficient and often dangerous. Every crevice is a potential escape route for prey. Every narrow gap a place where size becomes a liability rather than an advantage. And every ambush carries the risk of injury that could turn a dominant predator into a starving one. In this crowded labyrinth, the grouper's greatest strength is not its jaws or its size, but its ability to read the reef as a living map of possibilities, exits, and dead ends. As the camera follows a grouper gliding along a coral wall, the fish does not rush or charge, because speed would betray intention. Instead, it drifts with the confidence of an animal that understands its own presence is already a form of pressure, causing smaller fish to tighten their schools or dart nervously toward shelter. The reef fish know exactly where safety lies, or at least where it usually lies, because coral crevices and rocky holes have protected generations of prey from open water predators. These hiding spots are architectural marvels of nature, sculpted by erosion and biology into complex networks of tunnels, blind corners, and narrow chambers that favor long, flexible bodies and punish anything too large to maneuver inside. For most predators, these spaces are off-limits, frustrating sanctuaries that turn a failed chase into wasted energy. For the grouper, however, these same refuges represent an opportunity not to chase harder, but to think smarter. The grouper approaches the entrance of a crevice where a small reef fish has vanished, hovering with uncanny stillness, as if calculating angles invisible to the casual observer. Its large eyes track subtle movements, shadows flickering deep inside the coral, while its body position blocks the most obvious escape route back into open water. This moment is critical, because if the grouper lunges blindly, the prey will slip deeper into the maze, and the predator will gain nothing but exhaustion. Instead of attacking, the grouper performs a behavior that until recently was dismissed as coincidence or misinterpretation. A series of deliberate body signals that transform the hunt into something far more complex than solitary pursuit. The fish tilts its head, hovers precisely at the crevice opening, and performs a slow, exaggerated shaking motion, as if pointing without a finger, directing attention to a specific hole in the reef. This gesture is not aimed at the prey, nor is it a display meant to intimidate competitors, because its intended audience is a very different predator altogether. From the shadows emerges a Moray eel, its elongated body undulating with serpentine grace, its mouth opening and closing in a perpetual display that looks threatening but serves a physiological purpose. Moray eels are masters of the narrow spaces that defeat bulkier hunters, possessing flexible skeletons, reduced fins, and muscular bodies designed to probe deep into coral structures where prey believe themselves untouchable. The grouper's signal functions as an invitation, a visual cue that communicates not emotion or friendship, but location and opportunity. The eel understands this cue not because of shared ancestry or social bonding, but because natural selection has rewarded individuals that recognize and respond to it. As the eel approaches the indicated crevice, the grouper adjusts its position with subtle precision, shifting just enough to block alternative exits while leaving the eel a clear path into the reef's interior. What follows is not chaos, but choreography, an unspoken division of labor that turns the reef into a controlled environment rather than a random battlefield. The Moray slides inside the crevice, its body compressing and twisting through narrow passages with terrifying ease, while the grouper remains outside, hovering like a living barricade. Inside the coral, prey fish face a sudden and catastrophic reversal of fortune, because the hiding place that once offered safety has now become a corridor of panic. Driven forward by the eel's invasive presence, the prey is forced toward the only remaining exit, which opens directly into the waiting jaws of the grouper. This two-door trap is devastatingly effective, not because it relies on speed or surprise alone, but because it collapses the prey's options to zero. In ecological terms, the grouper controls the open water domain, using its size and jaw strength to dominate space beyond the reef, while the eel controls the cryptic domain, penetrating areas that would otherwise remain inaccessible. Each predator operates in the environment where it is most efficient, minimizing energy expenditure and reducing the risk of injury that comes with reckless pursuit. The prey caught between these complementary threats is not simply hunted, but strategically displaced, herded from perceived safety into certain death. The reef, usually a complex refuge, becomes a funnel, and survival becomes a matter of seconds rather than skill. What makes this interaction remarkable is not merely its effectiveness, but the fact that it occurs between species that are not genetically related, do not share social bonds, and gain nothing from loyalty beyond immediate payoff. This is not cooperation born of kinship or long-term alliance, but a transactional partnership shaped entirely by evolutionary advantage. Each participant benefits independently, because both the grouper and the eel increase their hunting success without increasing effort or danger. Studies have shown that groupers initiate these hunts more frequently when prey density is high and suitable eels are nearby, suggesting an ability to assess context and modify behavior accordingly, rather than relying on fixed instinct alone. The eel, for its part, is not a passive tool in this arrangement, but an active participant that benefits equally from the exchange. By entering the crevice with the grouper guarding the exit, the eel reduces the chance that prey will slip past it into open water, where its elongated body would be at a disadvantage. The presence of the grouper effectively seals the environment, allowing the eel to hunt with confidence rather than urgency. This mutual benefit explains why the interaction persists without the need for trust, memory of individuals, or repeated partnerships. The reef provides endless opportunities for these encounters, and natural selection ensures that individuals capable of recognizing and exploiting them survive more often than those that cannot. From a biological perspective, this behavior challenges traditional assumptions about intelligence and cooperation in fish, because it demonstrates an ability to use signals intentionally, interpret the actions of another species, and adjust behavior dynamically in response to environmental conditions. The grouper does not simply follow a script encoded at birth, but reacts to the presence or absence of potential partners, modifying its hunting strategy based on opportunity. This level of behavioral flexibility suggests that cognition in reef fish is more complex than once believed, shaped by the demands of living in one of the most structurally intricate ecosystems on the planet. The reef itself plays a central role in shaping this interaction, because without its dense architecture of coral and rock, such cooperation would be unnecessary. In open environments, predators rely on speed, endurance, or sheer numbers, but in the reef, success depends on spatial awareness and the ability to manipulate movement through constrained pathways. The grouper's bulk, often viewed as a disadvantage in tight spaces, becomes an asset when used to block exits and dominate territory, while the eel's flexibility transforms narrow crevices into hunting grounds rather than sanctuaries. Together, they exploit the reef's complexity rather than being limited by it, turning structure into strategy. This behavior also reveals a darker truth about evolution, because it underscores that intelligence does not require empathy, and cooperation does not imply morality. The grouper does not assist the eel out of goodwill, nor does the eel respond out of obligation, because neither species possesses a concept of fairness or loyalty as humans understand it. Their interaction is driven by immediate benefit, a calculation shaped by millions of years of selection, favoring individuals that waste less energy and take fewer risks. If conditions change, if prey density drops or eels become scarce, the behavior fades without consequence, replaced by solitary hunting or alternative strategies better suited to the moment. For the prey species, this partnership represents a terrifying escalation of predation pressure, because it nullifies behaviors that once guaranteed survival. Hiding, a strategy that evolved precisely to counter large predators, becomes ineffective when the predator recruits a specialist to invade those refuges. This arms race drives further adaptations, such as more complex escape routes, heightened vigilance, or changes in habitat use, illustrating how a single behavioral innovation can ripple through an ecosystem, reshaping interactions far beyond the immediate participants. The reef is not static, but a constantly evolving arena where strategies rise and fall based on who learns faster and who adapts more efficiently. As the hunt concludes and the grouper swallows its prize with a slow, effortless motion, the eel slips back into the reef's shadows, its role completed without acknowledgement or ceremony. There is no sharing of the meal, no display of alliance, only the quiet reset of a system optimized for survival. Moments later, the grouper resumes its patrol, scanning the reef for the next opportunity, while the eel disappears into the coral maze, both predators returning to their solitary existence until conditions align again. The cooperation, brief and precise, leaves no trace beyond its outcome, because in nature success is measured not by spectacle, but by efficiency. This behavior forces a re-evaluation of how intelligence and cooperation are defined in the animal kingdom, because it demonstrates that complex problem-solving can emerge in creatures without large brains or social hierarchies. The grouper does not need to remember individual eels or plan future hunts, because the environment itself provides the framework for interaction, and natural selection has refined the signals and responses until they function with minimal cognitive overhead. The result is a system that appears almost strategic, yet operates without conscious planning in the human sense, driven instead by instinct, shaped by experience and feedback. In the end, the grouper's recruitment of the Moray eel is not a story of friendship or alliance, but a demonstration of how evolution rewards efficiency above all else. It reveals a reef where predators do not merely chase, but manipulate space, exploit complementary strengths, and transform the environment into a weapon. The true menace of this behavior lies not in its brutality, but in its elegance, because it shows that even in the silent world beneath the waves, intelligence can manifest as collaboration across species boundaries, driven not by social bonds, but by the relentless logic of survival. The reef does not advertise its danger openly, because most of its violence happens in silence, inside spaces too narrow for spectacle and too tight for dramatic chases. From a distance, coral structures look like solid fortresses, colorful and immobile, promising refuge to anything small enough to slip inside. To prey species, these cracks and tunnels are escape hatches, refined by generations of natural selection, places where speed-based predators lose their advantage and bulk becomes a curse rather than a strength. Yet hidden within this architecture is a specialist that turns the reef's own defenses into liabilities, a predator whose entire body is engineered not for pursuit, but for intrusion. The Moray eel does not chase prey across open water or rely on sudden bursts of speed, because its power lies elsewhere, in the ability to go exactly where escape is supposed to be guaranteed. The Moray's form immediately betrays its purpose, because nothing about its elongated, fin-reduced body suggests efficiency in open water. It moves with a sinuous, almost deliberate rhythm, sliding rather than swimming, conserving energy by hugging surfaces and edges rather than cutting through the water column. This shape is not an accident of ancestry, but a functional solution to one of the reef's greatest challenges, which is access. Where other predators are stopped cold by narrowing passages and sharp turns, the Moray advances, compressing its body laterally, anchoring itself against rough coral surfaces, and pulling forward with powerful axial muscles that convert friction into leverage. Every inch of its anatomy is optimized for tight spaces, from its reduced pectoral fins that would otherwise snag on rock, to its thick, muscular skin that resists abrasion as it forces its way into the reef's most inaccessible chambers. As the eel enters a crevice, the camera follows closely, revealing a world of darkness and confinement that few predators can exploit. Light fades quickly, replaced by shifting shadows and the faint movements of trapped water, while the eel's head probes forward with unsettling confidence. Inside these spaces, vision becomes unreliable, because angles distort perception and prey remain hidden behind bends and outcroppings. The Moray compensates with an extraordinary sense of smell, relying on chemical cues dissolved in the water to track prey that it cannot see. Unlike many reef fish that depend heavily on sight, Morays possess a highly developed olfactory system, allowing them to detect minute traces of scent left behind by fleeing prey, effectively following an invisible trail through the coral maze. This reliance on smell transforms the concept of hiding, because while prey may be invisible, they are never odorless. Stress, movement, and injury all release chemical signals into the water, and within the enclosed spaces of the reef, these cues accumulate rather than dispersing. The Moray advances slowly, not because it is uncertain, but because speed would disrupt its sensory input, creating turbulence that smears the very information it depends on. Instead, it pauses, tests the water with subtle head movements, and adjusts its trajectory based on gradients of scent that grow stronger with each body length gained. To prey trapped ahead, this approach is deeply unsettling, because escape holes that once promised safety now funnel them toward a predator that cannot be outrun and cannot be hidden from. The intimidation factor of a Moray eel is not limited to its physical presence, but extends to the psychological impact it has on other reef inhabitants. Many fish, including species large enough to fend off other predators, hesitate to enter tight reef structures once a Moray is inside, because the eel's mode of attack is fundamentally different. In open water, threats are visible, directional, and often avoidable through speed or maneuverability. Inside the reef, however, the eel transforms the environment into a hostile zone, where visibility collapses, movement is restricted, and escape options vanish with each twist of the tunnel. Even large fish understand this implicitly, avoiding crevices occupied by Morays, because a confined encounter strips them of their advantages and exposes them to sudden, close-range strikes. The Moray's jaws add another layer of danger, because unlike most fish, it possesses a second set of pharyngeal jaws capable of lunging forward from the throat to grasp prey. This adaptation allows the eel to secure and pull prey deeper into confined spaces where struggling is futile, a critical advantage when hunting in environments that do not allow wide mouth opening or rapid head movements. In the reef's narrow corridors, this mechanism turns the eel into a living trap, capable of seizing prey with terrifying efficiency once contact is made. For prey species, the presence of a Moray inside a hiding place does not simply raise the risk of predation, but fundamentally invalidates the concept of refuge itself. Despite these formidable abilities, the Moray eel carries a significant limitation that shapes its behavior and partnerships, because in open water it is slow, exposed, and vulnerable. Its elongated body, so effective in confined spaces, becomes a liability when forced into pursuit across open reef flats or water columns where faster fish can easily outmaneuver it. The eel cannot chase for long distances, nor can it quickly retreat if confronted by larger predators in the open. This weakness creates a narrow ecological niche, one where success depends on ambush, intrusion, and environmental control rather than pursuit. Left alone, the Moray must rely on chance encounters, waiting for prey to make the mistake of entering its domain. This is where the presence of a grouper transforms the Moray's hunting prospects entirely, turning individual limitations into collective advantage. When a grouper patrols nearby, the eel's world expands beyond the confines of the reef's interior, because the open water chase is no longer its responsibility. The grouper, with its powerful bursts of speed and ability to dominate space outside the reef, becomes the mobile barrier that the eel lacks. Together, they create a closed system in which prey movement is predicted, constrained, and ultimately controlled. The eel flushes prey from hiding, exploiting its lockpick body and sensory precision, while the grouper intercepts any escape attempt into open water, sealing the outcome before it unfolds. In this joint hunt, the Moray's intimidation factor becomes a strategic tool rather than a byproduct of its presence. Prey fish confronted by an advancing eel inside a crevice experience a sudden reversal of threat dynamics, because retreat deeper into the reef leads toward the eel's jaws, while retreat outward leads directly into the grouper's ambush zone. Panic accelerates poor decision-making, causing prey to bolt toward what appears to be open safety, only to collide with a predator positioned precisely to capitalize on that reaction. The eel does not need to be fast or aggressive in these moments, because its role is not to kill directly, but to destabilize and displace prey, forcing them into predictable paths. From an ecological perspective, This interaction represents a remarkable example of complementary specialization, where two predators with vastly different morphologies and limitations form a temporary functional unit that is more effective than either species alone. The Moray's intrusion capability pairs seamlessly with the grouper's interception power, creating a hunting strategy that minimizes energy expenditure and reduces risk for both participants. The eel avoids dangerous open water pursuits, while the grouper avoids injury-prone attempts to extract prey from narrow crevices. Each predator operates within its optimal performance zone, leveraging the other to neutralize its weaknesses without the need for long-term bonds or complex social structures. What makes this arrangement particularly striking is its transactional nature, because there is no sharing of prey, no coordinated timing beyond immediate cues, and no dependence on repeated interactions with specific individuals. The reef itself facilitates these encounters, bringing predators into proximity through shared habitat use and overlapping prey interests. When conditions align, such as high prey density and available shelter, the partnership emerges organically, driven by opportunity rather than obligation. When conditions change, the interaction dissolves just as quickly, leaving both species to resume their solitary hunting strategies without consequence. The concept of the moray as the reef's lockpick captures the essence of its ecological role because it does not overpower defenses through force, but bypasses them through access. The reef's cracks, once thought to be inviolable sanctuaries, become liabilities in the presence of an animal designed to exploit confinement. This forces prey species to constantly reassess their behavior, balancing the risk of open water exposure against the danger of hiding places that may already be compromised. Over evolutionary time, this pressure shapes not only individual survival strategies, but the architecture of the reef itself, as prey species influence coral growth patterns through grazing and movement, indirectly altering the spaces predators use to hunt. In the broader context of reef ecology, the moray eel occupies a critical niche as a regulator of cryptic prey populations, targeting individuals that rely too heavily on hiding and reducing overcrowding within reef structures. By flushing prey into the open, often into the path of larger predators, the eel indirectly influences energy transfer across the ecosystem, linking hidden microhabitats with open water food webs. This role underscores the importance of behavioral diversity among predators, because it is not size or speed alone that determines ecological impact, but the ability to exploit underused dimensions of the environment. Seen through this lens, the joint hunt between moray eel and grouper resembles a business deal rather than a partnership, because each participant provides a service the other lacks. The eel supplies access and intimidation, penetrating spaces where prey believe themselves untouchable, while the grouper supplies containment and capture, controlling the exits that the eel cannot guard. There is no loyalty in this arrangement, only efficiency, and no trust beyond the immediate logic of mutual benefit. The reef becomes a marketplace of opportunity, where temporary alliances form and dissolve based on the shifting balance of risk and reward. As the eel withdraws from the crevice after a successful flush, slipping back into the shadows with unhurried confidence, the reef returns to its deceptive calm. Prey scatter, regroup, and resume their routines, while predators drift apart, their brief collaboration complete. Yet the impact of that interaction lingers, reshaping movement patterns and reinforcing the silent rules that govern life in the coral maze. In this world, survival does not belong to the fastest or the strongest alone, but to those capable of turning the environment itself into a weapon, using access, intimidation, and cooperation to collapse the illusion of safety. The open ocean often gives the illusion of emptiness, a vast blue expanse where life appears scattered and encounters seem accidental. Yet beneath that surface lies one of the most strategically organized predator systems on the planet. Orcas move through this environment not as solitary hunters reacting moment to moment, but as coordinated units that treat the ocean like a three-dimensional battlefield shaped by currents, coastlines, ice edges, and the predictable behaviors of their prey. Every pod carries a history of learned tactics, passed across generations, refined through repetition, and adjusted to local conditions, making each hunting event less of a chase and more of a planned operation unfolding in real time. Their power does not come merely from size or strength, but from foresight, role specialization, and an ability to break complex problems into manageable steps executed collectively. As a pod moves through coastal waters, there is an unmistakable sense of order to their motion, even when they appear playful or relaxed. Individuals maintain spacing that allows constant acoustic contact while avoiding interference. Their echolocation clicks, forming an invisible communication network that maps both prey and pod mates with extraordinary precision. When a hunt begins, this casual formation tightens, and roles emerge without any visible signal, because these assignments are not negotiated on the spot, but ingrained through shared experience. Some individuals accelerate forward to act as chasers, applying pressure that drives prey in a desired direction, while others drift outward to become blockers, sealing off escape routes that would otherwise lead to open water or deeper refuge. A final group positions itself for interception, conserving energy until the moment arrives to end the pursuit decisively. This division of labor transforms predation into a collective effort that minimizes risk and maximizes efficiency, turning the hunt into something closer to a coordinated sport than a chaotic struggle. Prey animals, whether fish schools, seals, or large marine mammals, do not face a single attacker, but a shifting perimeter that adapts to their responses. Attempts to dive deeper are countered by individuals positioned below, while sudden turns toward the surface meet others already anticipating the move. The ocean, which usually offers endless escape routes, becomes constrained by intelligence rather than physical barriers, as the pod continuously reshapes the space around its target. In this environment, speed alone is insufficient, because every burst of movement feeds new information back to the orcas, refining their predictions and tightening the net. The effectiveness of this approach becomes even more apparent when considering how orcas interact with other apex predators, including sharks that have long dominated marine food webs through fear and endurance. Documented cases of orca predation on large sharks, including great whites, have challenged deeply rooted assumptions about hierarchy in the ocean because they reveal a predator capable of dismantling even the most formidable defenses. These events are not random acts of aggression, but calculated interventions that exploit specific vulnerabilities, beginning with the orca's ability to disorient sharks through repeated ramming or precise positioning that induces tonic immobility. By flipping a shark onto its back, the orcas temporarily paralyze it, neutralizing speed, bite force, and escape potential in a single maneuver. What follows is perhaps the most unsettling aspect of these encounters, because the orcas do not consume the entire animal, nor do they attack indiscriminately. Instead, they target a specific organ, the liver, extracting it with remarkable precision before abandoning the rest of the carcass. To human observers, this behavior appears almost surgical, raising uncomfortable comparisons to deliberate selection rather than instinctive feeding. Yet when examined through the lens of biology and energy economics, the logic becomes clear. Shark livers are extremely rich in lipids, representing a dense, high-energy food source that offers maximum caloric return for minimal effort. By focusing on this organ, orcas optimize their intake, gaining substantial energy without the risks associated with prolonged struggle or consuming less nutritious tissue. This selective feeding strategy underscores a critical principle in predator ecology, which is that efficiency often outweighs completeness. For large, intelligent predators, the goal is not to consume everything available, but to extract the greatest benefit at the lowest cost, preserving energy for future hunts and reducing exposure to injury. Orcas, with their high metabolic demands and complex social structures, operate under strict energetic constraints that favor precision over excess. The apparent brutality of leaving a partially consumed shark behind is not wasteful, but economical, reflecting a deep alignment between behavior and biological necessity, rather than a lapse in predatory instinct. The implications of this behavior extend far beyond individual encounters, because the removal of apex predators from an ecosystem triggers cascading effects that reshape entire food webs. In regions where orcas have begun targeting sharks, researchers have observed dramatic changes in shark presence, with individuals abandoning traditional hunting grounds and altering migration patterns to avoid areas associated with orca activity. This displacement affects prey species that sharks once controlled, allowing some populations to expand while others face increased competition or predation pressure from alternative predators. In this way, orcas exert influence not just through direct consumption, but through fear-driven behavioral modification, effectively redesigning ecosystems by forcing other predators to adapt or retreat. This capacity to reshape ecological dynamics reflects the orca's broader role as planners rather than mere hunters, because their choices ripple outward through the environment, altering relationships among species that may never encounter an orca directly. By adjusting their menu to include or exclude certain prey, orcas can relieve or intensify pressure on specific populations, indirectly shaping habitat use, breeding success, and even the physical structure of ecosystems over time. Kelp forests, for example, can expand or contract depending on whether their primary grazers are kept in check by intermediate predators influenced by orca activity. These changes illustrate how top predators act as architects of ecological balance, not through constant presence, but through strategic impact. The planning evident in orca hunting extends beyond prey selection to the transmission of knowledge across generations, ensuring that successful strategies persist and evolve. Young orcas learn by observing and participating in hunts alongside experienced adults, gradually absorbing the nuances of timing, positioning, and prey behavior that define their pod's unique approach. This cultural transmission allows pods to specialize in particular prey types or environments, creating distinct ecological niches that reduce competition between groups and enhance overall survival. Some pods focus on fish, others on marine mammals, and still others on complex tactics like wave-washing seals from ice flows, demonstrating a level of behavioral diversity unmatched among marine predators. Such specialization reinforces the idea that orcas are not constrained by a fixed predatory identity, but possess the flexibility to adapt their strategies as conditions change. This adaptability becomes especially significant in a rapidly changing ocean, where climate shifts, overfishing, and habitat alteration continuously reshape prey availability. Orcas capable of modifying their diet and hunting methods are better positioned to persist because they are not dependent on a single resource or tactic. Their planning extends into the future not through conscious foresight, but through behavioral plasticity honed by evolutionary pressure, favoring those who can respond creatively to uncertainty. The idea that a predator can redesign its menu carries profound implications, because it suggests control over ecological narratives rather than passive participation in them. When orcas incorporate new prey into their diet or abandon old ones, they are not simply reacting to scarcity, but exploring opportunities that alter competitive relationships throughout the food web. This ability to pivot challenges the notion of static ecological roles, revealing instead a dynamic system where intelligence and learning can amplify evolutionary potential. Orcas become agents of change, capable of initiating shifts that reverberate across trophic levels, reshaping patterns of abundance and scarcity in ways that may persist for decades. In the vastness of the ocean, where encounters often seem fleeting and unstructured, the presence of such planners introduces an element of intentionality that feels almost unsettling. Orcas demonstrate that predation can be organized, selective and adaptive, blending physical dominance with cognitive sophistication to produce outcomes that extend far beyond the immediate act of feeding. Their coordinated roles, strategic targeting of energy-rich organs, and capacity to influence ecosystem structure position them not merely as apex predators, but as regulators of marine systems whose decisions shape the lives of countless other species. Ultimately, the orca's power lies not in any single trait, but in the integration of many, from social cohesion and communication to anatomical strength and metabolic strategy. By operating as teams that divide tasks, anticipate responses, and exploit vulnerabilities with precision, they transform hunting into a process of design rather than reaction. When such a predator can adjust what it eats and how it eats, it gains the ability to redefine relationships across the ocean, reminding us that intelligence in nature is not measured by tools or technology, but by the capacity to adapt, coordinate, and reshape the living world from the top down. Shallow coastal waters often appear deceptively simple, a place where depth is limited, visibility is high, and the rules of predation seem straightforward. Fish scatter across sandy flats, mangrove roots cast broken shadows, and sunlight penetrates almost to the bottom, exposing movements that would remain hidden in deeper water. Yet this apparent openness hides a different kind of complexity, one defined not by vertical escape, but by constraints, where speed loses its advantage and precision becomes everything. In this environment, dolphins thrive not because they are faster than everything else, but because they understand how to impose structure on chaos, turning featureless seafloors into controlled arenas where prey behavior can be predicted, manipulated, and exploited. Dolphins enter these shallow zones with an awareness that solitary hunting would be inefficient and often unsuccessful. Fish in shallow water have fewer vertical escape options, but they compensate with rapid directional changes and tight schooling behavior that can confuse a lone predator. A single dolphin charging into such a school would expend energy with little return, scattering prey without securing a kill. Instead, dolphins operate with a shared understanding that success here depends on coordination, timing, and role specialization. Their hunts unfold less like chases and more like planned confrontations, where individuals commit to specific tasks that only make sense in the context of the group's collective goal. One of the most striking examples of this strategy is mud ring feeding, a behavior that transforms the very substrate of the environment into a hunting tool. In this tactic, a designated dolphin swims in a tight circle near the seafloor, beating its tail forcefully to stir up sediment and create a rising wall of mud. The motion is deliberate and controlled, forming a near-perfect ring that expands upward through the water column like a living barrier. For the fish trapped inside, this cloud is more than visual confusion, because the suspended sediment interferes with sensory perception, masking escape routes and amplifying panic. The ring does not need to be solid, because the illusion of enclosure is enough to trigger a predictable response. As the mud ring rises, other dolphins take up positions just outside the circle, their bodies angled upward, eyes and sonar trained on the churning interior. These individuals do not contribute to the sediment work, conserving energy and maintaining readiness for the moment that matters. Inside the ring, fish attempt to flee horizontally, only to encounter the murky wall that appears impenetrable. With lateral escape blocked and depth limited by the shallow water, the fish resort to a final option, launching themselves into the air in a desperate bid to escape the unseen threat below. This is precisely the outcome the dolphins have engineered, because a fish in midair has no cover, no maneuverability, and no protection against a predator already positioned to intercept. The dolphins stationed around the ring surge upward in near-perfect synchronization, snatching fish from the air with minimal effort. Each individual takes turns, avoiding collision and competition, because the group's success depends on maintaining order rather than scrambling for advantage. The dolphin that created the ring does not rush in prematurely, because its role has already contributed to the outcome, and it will share in the payoff through repeated opportunities. This shared labor produces shared reward, reinforcing cooperation as the most effective strategy rather than encouraging selfish behavior that would destabilize the system. What makes mud ring feeding particularly compelling is that it is not an instinctual behavior hardwired into every dolphin, but a learned tactic that spreads through populations via social transmission. Young dolphins observe experienced adults performing the maneuver, gradually learning the precise tail movements, circle size, and timing required to create an effective trap. Over time, entire communities adopt the technique, refining it to local conditions such as sediment type, water depth, and prey species. This cultural inheritance allows dolphins to adapt rapidly to new environments, passing along solutions that evolution alone would take generations to encode genetically. The existence of such culturally transmitted hunting strategies challenges simplistic views of dolphins as merely playful or opportunistic feeders. Instead, it reveals societies structured around shared knowledge, where individuals benefit from group membership not only through protection or companionship, but through access to accumulated expertise. Dolphins that master cooperative techniques gain access to food resources that would otherwise be unavailable, increasing survival and reproductive success. Those that fail to learn or participate effectively are left at a disadvantage, reinforcing the importance of social bonds and conformity to group norms. Shallow water magnifies the value of these strategies because it strips away the advantages that speed and endurance provide in open ocean environments. In deeper water, dolphins can rely on rapid acceleration, prolonged pursuit, and three-dimensional maneuvering to exhaust prey. In contrast, shallow flats compress movement into a narrow vertical band, allowing fish to exploit sudden turns and tight schools to evade capture. Teamwork compensates for this limitation by replacing raw speed with control, ensuring that prey movements remain predictable and confined. By shaping the environment rather than reacting to it, dolphins convert constraint into opportunity. The sensory abilities that underpin these hunts further illustrate how biology and behavior intersect. Dolphins use echolocation to track fish even within turbid water, adjusting click rates and frequencies to maintain resolution despite interference from sediment clouds. Their hearing is finely tuned to detect subtle changes in prey movement, allowing them to anticipate escape attempts before they occur. Vision, while useful near the surface, becomes secondary to these acoustic cues, highlighting the importance of multisensory integration in complex hunting scenarios. This sensory flexibility ensures that even when visibility collapses, coordination remains intact. From an ecological perspective, these cooperative tactics exert significant pressure on prey populations, influencing not just numbers, but behavior and habitat use. Fish that inhabit areas frequented by dolphins employing mud-ring feeding may alter their schooling patterns, timing of movement, or choice of feeding grounds to reduce vulnerability. Such changes ripple through the ecosystem, affecting predator-prey relationships at multiple levels and shaping the distribution of species across the landscape. Dolphins, through their learned behaviors, become agents of ecological structuring rather than passive participants in a static system. The comparison of dolphin hunting groups to organized human collectives is tempting, but the reality is more subtle and more instructive. Dolphins do not plan in the abstract or assign roles through conscious deliberation, yet their repeated interactions produce stable patterns of cooperation that function as rules. Individuals understand when to create the ring, when to wait, and when to strike, because deviations from these patterns reduce success for everyone involved. Over time, selection favors dolphins that adhere to these unwritten rules, reinforcing behaviors that align individual action with group benefit. This alignment blurs the line between individual and collective survival, demonstrating that intelligence in the wild often manifests as the ability to synchronize with others rather than dominate them. Dolphins that insist on acting alone or attempting to steal kills risk disrupting the hunt and losing access to future opportunities. Cooperation becomes self-enforcing, not through punishment or hierarchy, but through the simple arithmetic of success and failure. The group thrives when individuals play their part, and individuals thrive because the group exists. The cultural dimension of dolphin hunting adds another layer of complexity because it allows populations to diverge behaviorally even when they share similar environments. Some groups specialize in shallow water techniques like mud-ring feeding, while others develop different cooperative methods suited to reefs, channels, or open water. These differences persist across generations, creating distinct hunting traditions that reflect local challenges and opportunities. Such diversity underscores the adaptability of dolphins as predators, capable of tailoring their strategies to the demands of their surroundings through learning rather than genetic change alone. By framing dolphins as tactical rather than cute, a clearer picture emerges of their place in the marine world. Their streamlined bodies, expressive faces, and apparent playfulness often obscure the reality that they are highly effective predators operating within a framework of shared rules and learned behaviors. The same intelligence that allows them to engage in social play also enables them to coordinate complex hunts, manipulate prey responses, and exploit environmental features with precision. Cuteness in this context is an accidental byproduct of mammalian features rather than an indicator of harmlessness. In the end, the image of dolphins encircling prey with a rising ring of mud captures the essence of their hunting philosophy. They do not rely on overwhelming force or relentless pursuit, but on cooperation, role specialization, and an understanding of how fear shapes movement. By working together, They transform shallow water from a limiting environment into a stage for tactical dominance, proving that success in nature often belongs to those who can organize rather than simply outrun. Dolphins are not defined by charm, but by strategy, and their true power lies in the quiet rules that govern how they hunt together. Cold, nutrient-rich waters stretch beneath the surface like an invisible engine room, driving some of the most productive ecosystems on Earth. Here, plankton blooms fuel immense food chains, drawing dense schools of small fish and krill into vast, shifting clouds that pulse with life. To a casual observer, these prey appear insignificant, tiny bodies moving en masse. Yet their collective speed, density, and unpredictability make them extraordinarily difficult to capture. For a predator the size of a humpback whale, raw power alone is useless in this environment because no amount of size can bite down on water itself. To survive here, giants must abandon brute force and instead weaponize physics, geometry, and cooperation, transforming the fluid properties of the ocean into tools as precise as any claw or tooth. Humpback whales arrive in these feeding grounds after long migrations that drain their energy reserves, having traveled thousands of kilometers from tropical breeding areas to colder latitudes where food is abundant but fleeting. Their massive bodies, insulated by thick layers of blubber, are built to retain heat in frigid waters, allowing them to remain active in environments that would rapidly exhaust smaller or less adapted mammals. Yet even with this physiological advantage, every feeding opportunity matters, because humpbacks must consume enormous quantities of prey in a limited time window to sustain themselves through months of fasting. This pressure has shaped a hunting strategy that appears almost engineered, relying on cooperation and environmental manipulation rather than individual pursuit. As a group of humpbacks descends beneath a dense shoal of fish, their movements slow and become deliberate, each whale positioning itself with careful attention to depth and spacing. The water here is alive with motion, fish darting and compressing in response to subtle changes in pressure and sound. Humpbacks exploit this sensitivity, beginning the hunt not with speed, but with preparation. One or more whales start to release streams of bubbles from their blowholes, spiraling upward as they swim in widening circles beneath the prey. These bubbles rise rapidly, forming a shimmering curtain that expands toward the surface, encircling the fish in a translucent barrier that seems insubstantial, yet proves remarkably effective. The effectiveness of bubbles as a hunting tool lies in the way fish perceive and respond to their environment. Bubbles disrupt the flow of water, creating turbulence that interferes with lateral line sensing, a key system fish use to detect movement and pressure changes. At the same time, bubbles alter local oxygen concentrations and visual cues, producing a confusing, noisy boundary that fish instinctively avoid. To the prey, the bubble wall does not read as empty space, but as an impassable obstruction, prompting them to cluster inward rather than risk crossing it. With each pass of the whales below, the bubble net tightens, shrinking the prey's available escape routes until the shoal collapses into a dense, panicked mass. Inside this tightening ring, chaos intensifies. Fish accelerate, collide, and attempt to dive or scatter, but the geometry of the net leaves them nowhere to go. Depth offers no refuge because the whales have positioned themselves beneath the shoal, while horizontal escape is blocked by the rising bubble curtain. The ocean, usually an infinite three-dimensional space, becomes suddenly constrained, reduced to a vertical cylinder with no viable exits. This compression is not accidental, but the result of precise coordination as each whale adjusts its bubble output and swimming path to maintain the integrity of the net. A single gap would allow the shoal to spill outward, undoing the effort, so synchronization is critical. As the net reaches its tightest configuration, the whales execute the final phase of the hunt with explosive precision. Multiple humpbacks surge upward simultaneously through the center of the bubble ring, mouths agape, pleated throats expanding like massive parachutes as they engulf enormous volumes of water and prey. This moment is often described as dramatic, but it is also deeply mechanical. A coordinated release of stored energy, timed to maximize intake while minimizing effort. The whale's upward momentum carries them through the densest concentration of fish, ensuring that each mouthful delivers the highest possible caloric return. The spectacle of several humpbacks breaking the surface together, jaws wide, water cascading from their baleen plates, is not random feeding behavior, but the visible culmination of a carefully structured process. Baleen, those long keratinous fringes hanging from the upper jaw, act as a filtration system, allowing water to escape while trapping prey inside. As the whales close their mouths and expel the engulfed water, fish and krill are retained, swallowed in quantities that would be impossible to capture individually. The entire sequence, from bubble release to surface breach, unfolds in seconds, yet represents the outcome of minutes of preparation and coordination beneath the surface. What makes this strategy especially powerful is its scalability, because it works precisely because the prey is small, fast, and abundant. Individual fish are agile enough to evade a single predator, but their reliance on schooling behavior becomes a liability when confronted with a tactic that exploits their collective responses. The bubble net does not target individual escapees, but manipulates the group as a whole, turning cohesion into confinement. This inversion of prey strategy highlights a recurring theme in predator-prey evolution, where adaptations that provide safety under one set of conditions become weaknesses under another. From a physical perspective, bubble net feeding demonstrates an extraordinary understanding, whether conscious or instinctive, of fluid dynamics and animal behavior. Bubbles rise due to buoyancy, forming stable vertical structures that persist long enough to serve as barriers. Their reflective surfaces scatter light, creating visual confusion, while their movement generates acoustic noise that masks approaching predators. Humpbacks exploit all of these effects simultaneously, producing a multi-sensory trap that overwhelms the prey's ability to interpret its surroundings. This integration of physics and biology allows whales to punch far above what their size alone would suggest, converting subtle environmental properties into decisive advantages. Teamwork is the foundation of this strategy, because a single whale cannot create a complete and stable net on its own. The precision required to maintain bubble density, ring shape, and timing demands cooperation among multiple individuals, each contributing to the structure without direct communication visible to human observers. Acoustic cues likely play a role, as humpbacks are known for their complex vocalizations, which may help synchronize movements and coordinate depth changes during the hunt. These sounds, resonating through the water, add another layer of sensory manipulation, potentially influencing prey behavior while keeping pod members aligned. The social dimension of bubble net feeding extends beyond the immediate hunt, because this behavior is learned and transmitted within populations. Young humpbacks observe experienced adults participating in coordinated feeding events, gradually acquiring the skills and timing necessary to contribute effectively. Over time, entire groups refine their techniques, developing variations such as spiral nets or vertical curtains, depending on local conditions and prey species. This cultural transmission allows humpbacks to adapt their feeding strategies more rapidly than genetic evolution alone would permit, enhancing resilience in environments where prey availability can change unpredictably. Ecologically, the impact of bubble net feeding is significant because it enables humpbacks to exert strong top-down pressure on prey populations without overexploiting them. By targeting dense aggregations and feeding efficiently, whales reduce wasteful chases and limit unnecessary disturbance to surrounding areas. This efficiency supports a balanced dynamic where prey populations can rebound during periods of low predation pressure, while remaining regulated during peak feeding seasons. The whale's reliance on cooperation also reduces competition among individuals, distributing food more evenly across the group and reinforcing social cohesion. The cinematic nature of synchronized surfacing belies the underlying necessity driving the behavior, because even animals as large as humpback whales cannot rely on size alone to secure food in a fluid environment. Water offers no resistance to jaws closing on empty space, and prey that moves collectively can evade even the most powerful swimmers if approached without strategy. Bubble net feeding represents a solution to this challenge, one that leverages cooperation to overcome the limitations imposed by scale. It is a reminder that in the ocean, intelligence often manifests not as individual cunning, but as the ability to coordinate actions across bodies separated by distance and depth. This reliance on teamwork also underscores a broader truth about marine giants, which is that size does not equate to invulnerability. Humpbacks face significant energetic demands, environmental uncertainty, and competition from other predators, all of which require adaptive strategies to navigate successfully. Their feeding behavior reflects an evolutionary compromise, balancing the need to consume vast quantities of small prey with the constraints of movement, metabolism, and habitat. By turning bubbles into barriers and synchrony into a weapon, humpbacks resolve this tension with remarkable elegance. As the surface calms after a feeding event, ripples spreading outward from the whale's emergence, the ocean quickly resumes its appearance of tranquility. Fish scatter, plankton drifts, and the whales sink back into the depths, their massive forms fading into blue. Yet the memory of that coordinated strike lingers, a testament to the power of collaboration in an environment where isolation would mean failure. Bubble net feeding is not merely a curiosity or a visual spectacle, but a demonstration of how even the largest predators depend on shared effort and precise timing to survive. In the end, the lesson embedded in this behavior is both humbling and profound. Humpback whales, giants of the sea, cannot simply overpower their prey, because small and fast animals exploit the very medium the whales inhabit. To succeed, the whales must work together, aligning their movements and exploiting the physical properties of water itself. Their synchronized ascent through a shrinking ring of bubbles is not an accident, but a deliberate convergence of biology, physics, and social intelligence, proving that in the ocean, teamwork remains essential no matter how large you grow. The deep ocean begins where light gives up its authority, fading from blue into black until vision becomes irrelevant and sound replaces sight as the primary currency of survival. Here, pressure rises to crushing levels, temperatures drop toward near freezing, and the seafloor lies thousands of meters below, invisible and unreachable for most life. This is not an environment that rewards improvisation or brute force, because mistakes are unforgiving and energy is precious. In this world, sperm whales reign not by accident, but through specialization so extreme that it borders on alien, combining physical adaptations, acoustic mastery, and social intelligence into a system built for hunting where almost nothing else can follow. Sperm whales are not simply large whales that happen to dive deep. They are organisms fundamentally shaped by the demands of the abyss. Their massive heads house the spermaceti organ, a structure once misunderstood, but now recognized as a critical component in buoyancy control and sound production. As a whale descends, changes in blood flow and temperature alter the density of this organ, subtly adjusting buoyancy in a way that reduces the energetic cost of movement. This matters because deep dives are expensive in every sense, draining oxygen reserves, increasing pressure stress, and limiting the time available to hunt. A single inefficient dive can represent a significant metabolic loss, and over time, inefficiency becomes fatal. Descending into darkness, the sperm whale leaves behind a world where prey can be chased or cornered visually. At depth, there are no landmarks, no reference points, and no reliable light sources beyond bioluminescent flashes that serve more as distractions than guides. Instead, the whale clicks, producing the loudest biological sounds on the planet, pulses so powerful they can stun prey and map the environment with extraordinary precision. These clicks are not random bursts, but carefully timed emissions that create acoustic images of the surrounding space, revealing the shapes and movements of squid that would otherwise remain undetectable. Each click is both a probe and a declaration, announcing presence while gathering information in a realm where silence can be as dangerous as noise. Yet even with these formidable tools, sperm whales do not operate as isolated hunters detached from social structure. They belong to stable social units, typically composed of related females and their offspring, forming groups that persist for decades. Within these units, individuals remain in acoustic contact even when separated by vast vertical distances, using patterned sequences of clicks known as coders to maintain cohesion. These coders function as acoustic signatures, allowing whales to identify not only individuals, but membership within specific social groups, much like accents or dialects distinguish human communities. In the absence of visual cues, this sonic identity becomes essential, preventing fragmentation in an environment that constantly pulls individuals apart. For young sperm whales, this social system is not a convenience, but a lifeline. Calves are born into a world they cannot yet navigate alone, lacking the lung capacity, muscle efficiency, and experience required for extreme dives. By staying within the protective umbrella of the group, they gain access to knowledge accumulated across generations, learning when and where to dive, how to manage oxygen efficiently, and how to interpret acoustic information in a meaningful way. Older females, often referred to as matriarchs, play a critical role in this process, guiding movements and responding to threats with a calm that reflects decades of survival in hostile conditions. This transmission of knowledge is particularly important because the deep ocean is not uniformly rich. Productive hunting grounds shift with currents, seasons, and the vertical migration of prey species that rise and fall daily in response to light cycles far above. A whale that dives blindly without understanding these patterns risks wasting precious oxygen on empty water. By contrast, whales embedded within a social network benefit from shared information, reducing uncertainty and improving success rates. In this context, information becomes power, because knowing where to dive and when to surface can mean the difference between thriving and slowly starving. The risk calculus of deep diving shapes every aspect of sperm whale behavior. Each dive requires a careful balance between depth, duration, and recovery time at the surface, where oxygen stores are replenished and excess nitrogen is safely released. Dive too shallow, and prey density may be too low to justify the effort. Dive too deep or too long, and the risk of hypoxia, decompression stress, or disorientation increases dramatically. Social coordination helps mitigate these risks, as whales synchronize surface intervals and maintain awareness of each other's status through sound. If one whale encounters trouble, others can adjust their behavior, closing ranks or altering movement patterns to provide support. Communication in this environment is not limited to simple contact calls, but extends into complex sequences that appear to carry contextual meaning. Researchers have documented variations in coders associated with different social units, suggesting a level of cultural identity that transcends immediate utility. These acoustic traditions persist across generations, passed from mothers to calves, reinforcing group cohesion and continuity. While the precise meanings of these signals remain elusive, their structured repetition and consistency point toward a communication system more sophisticated than previously assumed for non-human animals. The idea that sperm whales possess a form of social language gains further weight when considering their cooperative responses to threats. When faced with predators such as large sharks or, historically, human hunters, sperm whales have been observed forming defensive formations, clustering with heads outward and calves protected at the center. Coordinating such behavior in near-total darkness requires rapid, reliable communication because visual alignment is impossible. Sound fills this gap, allowing whales to synchronize movements and maintain formation under pressure. This collective defense underscores the importance of social bonds, not only for feeding efficiency, but for survival against external threats. Energy economics further reinforce the value of cooperation. Deep dives consume enormous amounts of energy, and prey, such as large squid, while nutritious, are not guaranteed catches. Missed opportunities or inefficient pursuits quickly accumulate into deficits that compromise health and reproductive success. By sharing information and maintaining group cohesion, sperm whales reduce variance in individual success, smoothing out the highs and lows of foraging in an unpredictable environment. This buffering effect is particularly important for calves and juveniles, whose margins for error are much smaller than those of experienced adults. The physiological demands of deep diving also impose limits that shape social behavior. Sperm whales exhibit remarkable adaptations for oxygen management, including high concentrations of myoglobin in their muscles, allowing them to store oxygen directly where it is needed. Their heart rates slow dramatically during dives, conserving oxygen and prioritizing blood flow to essential organs. These responses are not instantaneous reflexes, but carefully regulated processes that benefit from experience and learning. Young whales refine these skills over years, guided by observation and participation within the group, rather than through trial and error alone. Within this framework, the sperm whale's acoustic world becomes not just a tool for hunting, but the backbone of its society. Clicks and coders weave a continuous thread of information through the darkness, linking individuals across space and time. This sonic tapestry allows whales to function as cohesive units, despite the physical separation imposed by depth and distance. It also enables the emergence of complex social structures that persist independently of immediate environmental conditions, anchoring identity in sound rather than place. There is an irony in the fact that the loudest hunters in the ocean operate in near silence from a visual perspective, unseen and often unknown, even as they reshape deep-sea ecosystems. Their predation exerts pressure on squid populations that, in turn, influence nutrient cycling and carbon transport through the water column. By feeding at depth and defecating closer to the surface, sperm whales contribute to the vertical movement of nutrients, linking deep and shallow systems in ways that ripple outward through the food web. Their ecological role extends beyond hunting, embedding them as engineers of oceanic processes that operate on planetary scales. The mystery surrounding sperm whale communication persists because much of their world remains inaccessible to human observation. The depths they frequent are hostile to prolonged study, and the nuances of acoustic signaling are difficult to decode without context that we can only partially reconstruct. Yet each discovery hints at a level of social complexity that challenges traditional assumptions about intelligence and language in non-human species. The patterned nature of coders, their stability across generations, and their apparent role in group identity suggest a communication system that goes beyond immediate survival needs. In the end, the sperm whale embodies a paradox of the deep ocean, combining brute physical power with delicate social coordination and solitary hunting with deep-rooted community. Their success lies not in domination through force alone, but in the careful management of risk through shared knowledge and collective behavior. In a realm where mistakes are magnified and resources are scarce, cooperation becomes the most reliable strategy, turning information into the ultimate currency of survival. As these whales rise slowly from the depths, lungs refilling with air beneath the open sky, their clicks continue to pulse through the water, carrying signals we are only beginning to understand. The ocean's loudest hunters reveal that volume does not preclude subtlety, and that beneath the thunder of their sonar lies a social world shaped by learning, tradition, and connection. In the darkness where vision fails, sound becomes language, and language becomes the thread that binds survival to society. Along the margins of ice, rock, and tide, seals occupy one of the most dangerous positions in the ocean, living precisely where predators and prey collide. These boundary zones, whether they are kelp forests, coastal shelves, or the broken edges of polar ice, concentrate life into narrow corridors where visibility is inconsistent and escape options are limited. For seals, survival depends not on dominance or aggression, but on anticipation, coordination, and an almost obsessive awareness of everything that moves nearby. They are neither apex predators nor helpless victims, but a deliberately tuned middle force that shapes how the entire system behaves. In this role, seals become something more than prey, because their success or failure determines which hunting strategies thrive and which predators evolve into something sharper. A seal resting at the surface rarely appears relaxed, even when its body language suggests calm. Heads rise and fall rhythmically, eyes scanning not just the waterline, but the space beneath it, because danger rarely announces itself from above. Their vision, adapted to function both in air and underwater, allows them to track movement across shifting light conditions, while sensitive whiskers detect pressure changes that betray approaching predators long before they are visible. These whiskers, known as vibrissae, are among the most refined sensory tools in the marine world, capable of detecting the faint hydrodynamic trails left by swimming animals minutes after they have passed. This sensory awareness turns stillness into vigilance, allowing seals to read the water like a map of recent activity rather than a blank surface. Seals rarely rely on individual awareness alone because isolation magnifies risk. Instead, they aggregate, forming loose groups that maintain spacing without collapsing into dense schools. This configuration balances the need for shared vigilance with the necessity of rapid individual movement, allowing seals to react independently while benefiting from collective awareness. When one seal shifts posture or changes swimming direction abruptly, others respond almost instantly, not because of conscious signaling, but because shared alertness amplifies small cues into group-wide reactions. In these moments, safety emerges not from strength, but from synchronization, as coordinated movement makes it harder for predators to single out a target. Timing plays an equally critical role in seal survival, particularly in environments where predators operate on predictable schedules. Many seal species adjust their movement patterns based on tides, light levels, and seasonal shifts in predator presence. They haul out on ice or rocks during periods when underwater threats are most active, conserving energy while minimizing exposure, then return to forage when conditions favor escape rather than pursuit. This temporal awareness transforms time into a defensive tool, allowing seals to exploit windows of relative safety created by environmental cycles beyond any single animal's control. Depth selection further refines this strategy, as seals often remain within specific water layers that balance access to food with escape potential. Too shallow, and they risk ambush from below. Too deep, and they lose the ability to surface quickly if threatened. By hovering within these optimal zones, seals maintain flexibility, able to dive or surface rapidly depending on the direction of danger. This constant negotiation between risk and reward defines seal behavior, shaping their movements into patterns that appear cautious, but are, in fact, finely calibrated responses to persistent threat. Despite these defenses, predictability carries its own cost, because any pattern repeated long enough becomes exploitable. Predators such as orcas excel not by overpowering seals directly, but by reading their habits and turning defensive strategies into traps. When seals cluster tightly near ice edges or rocky ledges, they reduce individual vulnerability, but create spatial bottlenecks that limit escape routes. Orcas exploit this by approaching slowly and deliberately, using their size and presence to apply pressure rather than force, nudging seals toward positions where their options collapse. Separation, not speed, becomes the goal, as a single isolated seal represents a dramatically easier target than a cohesive group. Once separation occurs, predators capitalize on geometry and angle rather than raw pursuit. By driving seals off ledges or ice flows into open water, orcas invert the seal's defensive advantage, transforming a safe resting platform into a launch point for attack. In water, seals are agile, but their escape relies on unpredictable movement and access to vertical space. Orcas counter this by positioning themselves to block preferred routes, forcing seals into shallow angles where acceleration is limited and maneuverability declines. The hunt becomes a spatial puzzle, solved not through aggression, but through constraint. Importantly, this interaction does not reflect seals failing to adapt or predators exploiting ignorance. Instead, it reveals a dynamic feedback loop, where each adjustment by one side reshapes the strategies of the other. Seals alter group size, spacing, and timing in response to increased predation pressure, while predators refine their methods to counter these changes. Over time, this iterative process produces increasingly sophisticated behaviors on both sides, elevating the entire system beyond simple predator-prey mechanics. Seals become, in effect, a training ground where predators are tested, refined, and selected for intelligence rather than brute force. This evolutionary pressure has tangible consequences, because predators that cannot solve the seal problem do not thrive. Orcas that fail to coordinate or misjudge seal behavior waste energy and risk injury, reducing their reproductive success. Conversely, individuals that learn to read seal movement patterns, anticipate reactions, and coordinate with pod members gain access to a high-energy food source that supports larger brains and more complex social structures. In this way, seals indirectly shape predator evolution, favoring cognitive flexibility and cooperation over solitary aggression. From the seal's perspective, intelligence is equally essential because surviving encounters requires rapid assessment and adaptation rather than reflexive flight. Seals learn to distinguish between different types of predators, adjusting their responses accordingly. A shark's approach triggers different movement patterns than an orca's presence, reflecting the distinct hunting styles and threat profiles of each predator. This discrimination allows seals to allocate energy efficiently, avoiding unnecessary panic while responding decisively to genuine danger. Such nuanced behavior underscores that seals are not passive participants in this system, but active decision-makers constantly evaluating risk. The ecological ripple effects of these interactions extend far beyond seals and their immediate predators. When seal populations alter their behavior, prey species experience changes in predation pressure, as seals adjust foraging locations and timing. Fish and invertebrates respond in turn, shifting distribution and abundance, which influences nutrient cycling and habitat structure. Predators, responding to seal availability, may redistribute themselves across regions, affecting competition and interactions among apex species. A single behavioral shift at the level of seals can propagate through multiple trophic layers, reshaping ecosystems in subtle but profound ways. This sensitivity highlights why seals function as keystone targets within marine food webs, not because of their biomass alone, but because of their role in driving adaptive behavior. Their presence forces predators to innovate, while their responses to predation shape the flow of energy across ecosystems. Remove seals, and predators lose a primary driver of cooperative hunting and strategic refinement. Alter seal behavior, and entire systems recalibrate in response, demonstrating the interconnectedness that defines marine ecology. Understanding this dynamic reframes how we view predator-prey relationships, moving beyond narratives of dominance and victimhood toward a recognition of mutual influence. Seals are not merely surviving despite predation, but actively shaping the conditions under which predation occurs. Their vigilance, grouping, and timing strategies impose constraints that predators must overcome, raising the bar for success and filtering out less adaptable hunters. In doing so, seals contribute to the evolution of intelligence and cooperation at the top of the food web. For viewers, this realization carries significance beyond academic interest, because it reveals the ocean as a living chessboard where every move prompts a counter-move and strategy evolves continuously. Seals occupy the center of this board, not as expendable pieces, but as catalysts that force the game forward. Their behavior influences which predators dominate, how ecosystems balance, and how energy moves through the system. In a changing ocean, where human activity alters habitats and food availability, understanding these relationships becomes essential for predicting and managing ecological outcomes. The story of seals is therefore not one of weakness, but of influence, illustrating how survival strategies at one level can drive complexity at another. By demanding smarter tactics from predators, seals elevate the entire system, ensuring that success belongs not to the strongest, but to the most adaptable. This ongoing exchange of strategy and counter-strategy defines the rhythm of marine life, reminding us that intelligence in nature often emerges not from dominance, but from the necessity of staying alive in a world that never stops testing its inhabitants. At the edge of the frozen world, where wind scours rock bare and the ocean gnaws relentlessly at ice, penguins gather in numbers that seem absurd until you understand the math of survival. From a distance, their colonies look chaotic, noisy, almost comedic, bodies packed shoulder to shoulder, heads bobbing, flippers flailing as if nature misplaced a crowd of clowns at the bottom of the earth. Yet nothing here is accidental. Every density pattern, every synchronized movement, every apparent awkward shuffle is the outcome of ruthless selection pressure imposed by cold, hunger, and predators that punish mistakes without mercy. Penguins survive not because they are individually exceptional, but because they have engineered collective solutions to problems that no single body could solve alone. Life on land is hostile before a single predator appears. Temperatures plunge well below freezing, wind strips heat faster than muscle can generate it, and exposed skin becomes a liability measured in minutes rather than hours. Penguins counter this not with speed or strength, but with proximity. Tight colonies form living insulation systems where bodies press together in shifting mosaics that trap warmth and reduce heat loss across the group. Individuals on the edge rotate inward over time, while those in the warmer center are gradually displaced outward. distributing thermal stress across the colony rather than allowing it to crush the weakest members first. This is not cooperation born of kindness, but necessity, because any penguin isolated from the group pays an immediate energetic price that can mean the difference between survival and collapse. The same logic governs predator defense, because penguins on land are slow, exposed and limited in escape options. Seabirds attack from above, while terrestrial predators exploit gaps along colony edges, searching for individuals forced out of position by fatigue or poor timing. By clustering tightly, penguins reduce the number of available targets and overwhelm predators with uniformity. When hundreds or thousands of near-identical bodies move together, it becomes difficult for an attacker to lock onto a single individual long enough to commit. Confusion becomes a shield, and anonymity becomes armor, because predators depend on isolating weakness, not confronting a wall of equivalent choices. This principle intensifies at the shoreline, where the real danger begins. The ocean is both pantry and battlefield, offering food in abundance, but demanding payment in risk. Penguins do not enter this space casually, because beneath the surface wait predators built for pursuit, interception, and ambush. Leopard seals, orcas, and large sharks exploit the moment penguins transition from land to water, when acceleration is limited and escape angles are constrained. Penguins respond by turning departure into a collective decision rather than an individual gamble. Groups gather at the water's edge, hesitating, peering downward, bodies tensing as if weighing invisible odds, because the first to enter bears the highest risk. This hesitation is not indecision, but information gathering. Penguins scan for disturbances in the water, subtle changes in surface texture, shadow movements below, or patterns that suggest a predator's presence. Only when enough individuals assess the risk as acceptable does the group commit, launching together in a synchronized surge that floods the entry point with bodies. This mass entry overwhelms predator targeting systems because timing collapses into chaos. Instead of one predictable prey item, predators are confronted with dozens moving at once, each one briefly exposed but immediately shielded by the density of the group. Once in the water, penguins transform from awkward walkers into precision swimmers, their torpedo-shaped bodies and rigid flippers perfectly suited for burst propulsion. They do not scatter randomly, because disorder increases vulnerability. Instead, they organize into loose formations that follow habitual routes, often referred to as traffic lanes, shaped by underwater topography, current flow, and predator distribution. These lanes are not marked physically, but remembered collectively, reinforced through repeated use across generations. By sticking to known pathways, penguins reduce uncertainty, minimize energy expenditure, and maintain group cohesion in an environment where separation can be fatal. Swimming in groups further complicates predator attacks by creating overlapping wakes and visual interference. Penguins rely on burst diving, rapid changes in depth and direction that exploit their ability to compress air and withstand pressure changes more effectively than many of their predators. A penguin pursued at the surface may suddenly dive steeply, then level out, then reverse direction, using vertical space as a defensive dimension. When dozens perform these maneuvers simultaneously, tracking becomes exponentially harder, forcing predators to either commit blindly or abandon the chase in favor of easier opportunities. Coordination extends even to foraging behavior. Penguins often feed together, herding schools of fish or krill toward the surface or into confined areas where escape routes collapse. While they lack the size to dominate prey individually, their numbers compensate, allowing them to exploit prey behaviors that favor aggregation under threat. Fish that might evade a single pursuer become trapped by collective pressure, mirroring the same principles that protect penguins from predation. In this way, teamwork operates symmetrically, shaping both offense and defense through shared movement and timing. The effectiveness of these strategies depends on balance within the ecosystem, because penguin survival is not determined by their behavior alone, but by the presence and absence of other predators. Apex predators play a stabilizing role by regulating mid-level predators that would otherwise exert disproportionate pressure on penguin populations. When orcas patrol coastal waters, for example, they suppress the activity and distribution of seals that specialize in penguin hunting. This top-down control creates windows of relative safety, allowing penguin colonies to thrive despite persistent risk. When that balance breaks, the consequences are swift and unforgiving. In regions where apex predators decline due to human activity, mid-level predators such as seals can surge in number and expand their hunting ranges. Seals are highly efficient penguin hunters, capable of exploiting the same shallow zones and traffic lanes penguins rely on for safety. Unlike apex predators, which may take penguins opportunistically, seals can specialize, learning colony locations, entry points, and timing patterns with precision. Under these conditions, penguin teamwork begins to fail, not because the strategy is flawed, but because it was never designed to withstand relentless pressure from an overabundant, highly focused predator. This breakdown reveals a critical truth about collective defense, which is that it depends on predictable levels of threat. Teamwork reduces risk by spreading it, but if predation intensity exceeds a certain threshold, spreading risk simply ensures widespread loss. Penguins confronted with excessive seal predation may alter departure timing, route selection, or colony placement. But these adjustments come with trade-offs that reduce feeding efficiency and reproductive success. Over time, populations decline not through dramatic collapse, but through accumulated energetic deficits that erode resilience generation by generation. Understanding penguins as survival engineers rather than comic figures reframes their behavior as active problem-solving rather than passive endurance. Their waddling gait on land is not evidence of incompetence, but a compromise shaped by the demands of swimming efficiency. Their dense colonies are not social indulgences, but thermodynamic and defensive structures. Their synchronized movements are not instinctive reflexes, but the product of selection, favoring individuals who align with group behavior rather than diverge from it. This perspective also clarifies why penguins are so sensitive to environmental change. Disruptions to sea ice, prey distribution, or predator balance undermine the assumptions built into their strategies. Traffic lanes become unsafe, departure timing loses reliability, and group size may shrink below the threshold needed to confuse predators effectively. Each of these changes chips away at the foundation of team defense, exposing individuals to risks they are poorly equipped to face alone. From an ecological standpoint, penguins occupy a pivotal position, translating changes at the top of the food web into visible population responses. Their success reflects not just their own adaptations, but the health and structure of the systems around them. When penguin colonies flourish, it often signals a balanced ecosystem where predation pressure, prey availability, and environmental conditions align within survivable bounds. When they falter, it is rarely due to a single factor, but to cascading failures across multiple levels of the food web. The image of penguins as cute or clumsy persists because their most intense battles are subtle, fought through timing, spacing, and restraint rather than violence. Yet beneath that surface lies a constant strategic contest where every movement carries consequence. Penguins do not survive by outrunning predators or overpowering them, but by refusing to present clean solutions. They blur targets, compress risk, and weaponize numbers, forcing predators to solve increasingly complex problems to succeed. In this light, team defense is not a metaphor, but a form of warfare governed by probability and pressure. Each synchronized dive, each collective hesitation at the water's edge, represents a calculation shaped by millions of years of loss and survival. Penguins are not protected by innocence or luck, but by systems refined to exploit the limits of predator perception and endurance. Their survival strategies remind us that in nature, cooperation is not softness, but strength, and that what looks like comedy from afar is often the product of relentless, invisible struggle. When penguins march together toward the sea, they are not performing for observers, but executing a doctrine honed under constant threat. Their lives unfold on a chessboard where every piece matters, and where teamwork is the only counter to forces larger, faster, and more lethal than any individual could face alone. In that context, their unity is not charming, but formidable. a reminder that in the ocean's harshest arenas, collective intelligence can rival raw power. Cold coastal waters along the northern Pacific margin rarely feel stable because every surge, tide, and current rearranges the balance between growth and collapse. Kelp forests rise and fall here, not as static underwater landscapes, but as living structures constantly threatened by grazers capable of stripping them down to bare rock in a matter of weeks. Into this volatile system enters an animal that looks almost improvised, floating on its back with paws in the air, fur puffed out like a life raft, yet operating with a level of ecological influence that far exceeds its size. Sea otters are not dominant through strength or speed, but through disruption, using intelligence, tools, and relentless appetite to rewrite the rules of their environment. A sea otter at rest is never truly idle. Even when floating calmly at the surface, its body drifts with purpose, paws constantly adjusting fur, whiskers sampling the water, lungs acting as buoyancy regulators that keep the animal suspended with minimal effort. This posture is not leisure, but efficiency, because life for an otter is defined by energy math that allows no margin for error. Without a thick layer of insulating blubber like other marine mammals, otters depend entirely on dense fur and constant metabolic heat production to survive cold waters. Their bodies burn fuel at a rate that would bankrupt most animals, forcing them to consume a substantial fraction of their own body mass in food every single day just to maintain equilibrium. This relentless energy demand shapes everything about how sea otters interact with their environment. They cannot afford to specialize narrowly or forage passively, because doing so risks starvation during periods of scarcity. Instead, otters become opportunists with standards, targeting prey that offers the highest return for effort while remaining accessible through skill rather than brute force. Hard-shelled invertebrates dominate their diet, including sea urchins, crabs, clams, and mussels, animals protected not by speed but by armor. Where many predators avoid such prey due to injury risk or wasted energy, otters lean into the challenge because their solution is not strength but technology. Tool use in sea otters is not a novelty or an occasional trick, but a core survival strategy refined over generations. An otter diving to the sea floor often selects a rock before even locating prey, tucking it into a loose fold of skin beneath its forelimb, a built-in storage pocket evolved specifically for this purpose. This choice is deliberate because suitable tools are not evenly distributed across the sea floor, and returning to the surface without one means lost opportunity. Once prey is captured, the otter resurfaces, positions the rock on its chest like an anvil, and brings the shell down with repeated, controlled strikes until it fractures cleanly. This behavior is not instinctive in the simple sense, because otter populations exhibit regional preferences in tool choice, prey selection, and striking technique that cannot be explained by genetics alone. Some otters favor flat stones, others rounded ones, and some populations show distinct habits of reusing particular tools, returning to the same rock again and again. Observations have shown otters stashing preferred stones in crevices or carrying them between foraging bouts, behavior that requires memory, foresight, and the ability to associate a specific object with future utility. These are hallmarks of culture rather than reflex. The transmission of these skills reinforces that distinction. Otter pups do not emerge fully formed as expert foragers because their early lives are marked by dependency and learning. Mothers invest enormous energy in teaching, bringing live prey to the surface and allowing pups to manipulate it, fail, and try again under supervision. Young otters observe tool selection, striking angles, and prey handling through repeated exposure, gradually refining their technique over time. This learning process varies between populations, creating localized traditions that persist across generations and adapt to available resources. In this way, otter intelligence becomes cumulative, building a shared library of solutions that allows populations to exploit environments more efficiently than raw instinct would permit. The ecological consequences of this behavior are profound, because sea otters do not simply consume prey, they regulate it with surgical precision, driven by hunger rather than balance. Sea urchins, in particular, represent a pivotal target, because unchecked urchin populations can devastate kelp forests by grazing them down to their holdfasts. In the absence of otters, urchins proliferate, transforming lush underwater forests into barren seascapes dominated by spiny grazers and exposed rock. This shift cascades through the ecosystem, reducing habitat complexity, lowering biodiversity, and altering nutrient cycling across the coastal shelf. When otters are present and actively foraging, this dynamic reverses. By preying heavily on urchins, otters relieve grazing pressure on kelp, allowing forests to regrow vertically and horizontally. Kelp can then slow currents, trap sediments, and provide shelter for fish, invertebrates, and juvenile organisms that would otherwise struggle to survive. The return of kelp reshapes light penetration, oxygen dynamics, and food availability, creating a layered ecosystem that supports far more life than an urchin-dominated landscape ever could. In this sense, otters form an indirect alliance with kelp forests, not through intention but through consequence. This alliance is fragile because it depends on the otter's ability to maintain relentless foraging pressure. A decline in otter numbers, whether through predation, disease, or human impact, allows urchins to rebound rapidly, undoing decades of ecological recovery in a short span of time. The system does not drift slowly toward imbalance, but snaps back abruptly, revealing how tightly coupled otter behavior is to ecosystem structure. Otters are therefore not merely consumers, but keystone agents whose presence or absence determines the architecture of entire coastal regions. Life within an otter raft illustrates how individual survival strategies scale into social dynamics. Otters often gather in floating groups, sometimes numbering in the dozens, anchoring themselves together with kelp strands to prevent drifting while resting. These rafts are not social displays, but energy-saving structures that reduce movement, conserve heat, and provide collective vigilance against predators. While resting, otters groom constantly, because the integrity of their fur is a matter of survival rather than comfort. Each hair must remain clean and properly aligned to trap insulating air, and even minor fouling can lead to hypothermia. This grooming behavior reinforces the metabolic trap otters live within. Every minute spent grooming is a minute not spent foraging, yet failure to groom increases heat loss and raises food requirements even further. Otters are therefore locked into a feedback loop where survival depends on balancing time between feeding, grooming, and rest with extraordinary precision. Their intelligence manifests not as leisure or curiosity, but as efficiency under pressure, optimizing behavior across competing demands that leave no room for waste. Predation risk adds another layer to this equation, because otters operate in zones frequented by sharks, orcas, and large terrestrial predators along coastlines. Their defense is not speed or aggression, but awareness, proximity to cover, and group vigilance. By remaining near kelp forests, otters gain access to structural complexity that interferes with predator movement and detection. Kelp fronds break up visual lines, dampen hydrodynamic signals, and provide vertical escape routes that otters can exploit quickly. In turn, healthy kelp forests owe their existence to otter predation on grazers, reinforcing the reciprocal nature of this relationship. This feedback loop highlights a broader truth about intelligence in ecological systems, which is that it often operates indirectly. Sea otters do not manage ecosystems intentionally, yet their tool use, dietary preferences, and learning behaviors generate outcomes that ripple outward across trophic levels. Their intelligence reshapes the battlefield not by confronting enemies directly, but by altering the conditions under which others operate. By removing urchins, they restore complexity. By restoring complexity, they change who can survive and thrive in the system. The chaos otters introduce is therefore productive rather than destructive, a controlled disturbance that prevents any single species from monopolizing resources. This stands in contrast to systems where key regulators are removed, allowing simplified, unstable states to dominate. Otters exemplify how behavioral flexibility and problem-solving can substitute for physical dominance, producing ecological effects that rival those of much larger predators. Viewing sea otters through this lens dissolves the illusion of softness created by their appearance. Their floating posture, expressive faces, and playful interactions mask a life defined by constant work, precise decision-making and unrelenting pressure to perform. Every dive, every cracked shell, every grooming session contributes to a chain of consequences that extends far beyond the individual animal. Otters are not merely surviving in their environment, they are engineering it through repeated intelligent action. In the end, the story of the sea otter challenges narrow definitions of intelligence that focus solely on hunting tactics or social dominance. Intelligence here is not about killing faster or outthinking prey in direct combat, but about altering systems so that success becomes more likely over time. By wielding tools, transmitting knowledge, and exploiting feedback loops between predators and habitat, sea otters demonstrate that reshaping the battlefield can be as powerful as winning individual fights. In cold coastal waters, where imbalance lurks constantly, their chaos is not a flaw, but a force that keeps life complex, resilient, and alive. The reef is often described as crowded, competitive, and loud, yet for an octopus it is something closer to a raw material rather than a fixed landscape. Where other animals navigate the reef as it exists, the octopus treats it as malleable, a shifting puzzle that can be reshaped moment by moment to suit its needs. In this environment of coral rubble, sand patches, algae mats, and fractured stone, survival does not belong exclusively to the fastest swimmer or the largest jaw, but to the organism capable of dissolving into background, rewriting angles, and turning complexity itself into a weapon. Octopuses do not rely on allies or coordinated packs, because their strength lies in becoming indistinguishable from the battlefield, merging perception, body, and terrain into a single adaptive system. An octopus resting in plain sight is rarely seen for what it is, because its skin operates as a live interface between internal decision-making and external reality. Within seconds, specialized pigment cells called chromatophores expand and contract under neural control, altering color patterns with a precision that rivals digital camouflage. Beneath them, layers of iridophores and leucophores reflect and scatter light, adding depth, sheen, and brightness modulation that responds to ambient conditions rather than simply matching hue. This visual transformation is only the first layer, because texture changes follow immediately, with muscular papillae rising or flattening to mimic the roughness of coral, the smoothness of sand, or the broken silhouette of rubble. The result is not imitation in the artistic sense, but functional disappearance, as the octopus collapses its outline until it ceases to read as an object at all. Posture completes the illusion. Arms fold, twist, or extend in asymmetrical arrangements that break recognizable body plans, aligning with the surrounding shapes rather than the animal's own anatomy. An octopus does not merely change color to match a rock. It becomes a rock-shaped absence of expectation, exploiting the way predators and prey alike scan environments for familiar cues. Vision-based hunters look for contrast, edges, and movement, and the octopus erases all three simultaneously. This is not a passive defense triggered by fear, but an active, continuous process of environmental reading and response, recalculated moment to moment as light shifts and currents stir debris. Camouflage, however, is only the foundation, not the strategy itself. Octopuses are hunters, and hunting demands engagement rather than disappearance alone. When moving through the reef, an octopus does not wander aimlessly, but scouts deliberately, extending arms ahead of its body to probe crevices, test holes, and sample chemical cues left behind by potential prey. Each arm functions as an independent sensor, equipped with taste receptors that allow the octopus to identify edible targets through touch alone. This distributed sensing allows the animal to build a spatial and chemical map of its surroundings without exposing its core body to danger. Rather than charging prey directly, the octopus manipulates space. It may gather shells, stones, or fragments of coral, stacking them to create partial barriers or hiding places that did not exist moments before. These constructions are not permanent structures but temporary solutions tailored to immediate needs, turning open areas into ambush zones and narrowing escape routes for crabs, fish, or mollusks. In some cases, octopuses have been observed carrying coconut shells or similar debris across open ground, assembling them into shelters that provide instant refuge when danger appears. This behavior demonstrates foresight and planning, qualities rarely associated with invertebrates, yet essential to surviving in exposed environments. During an ambush, the octopus becomes both wall and trap. Arms spread outward in a loose perimeter, blending seamlessly into the surrounding substrate, while the central body remains concealed. Prey entering this zone may not perceive threat until multiple arms converge simultaneously, sealing exits before contact even occurs. The capture itself is rapid and precise because suction cups grip with remarkable strength and sensitivity, allowing the octopus to restrain struggling prey without injuring itself. Venom delivered through a beak-like mouth paralyzes or kills efficiently, minimizing prolonged struggle that could attract attention from larger predators. What grants the octopus an almost unfair advantage in these encounters is the architecture of its nervous system. Unlike vertebrates, whose brains centralize decision-making, an octopus distributes a significant portion of its neurons into its arms. Each limb can process sensory input, coordinate movement, and respond reflexively without waiting for instructions from the central brain. In a fight or escape, this means arms react instantly to local conditions, adjusting grip, direction, or force independently. If one arm encounters resistance or danger, others can adapt simultaneously, producing fluid, multi-directional responses that appear improvisational but are grounded in parallel processing. This decentralization reduces reaction time and increases resilience, because damage or distraction in one area does not cripple the entire system. An octopus navigating a complex escape route can solve multiple spatial problems at once, with arms exploring alternative paths, retracting from threats, and pushing against surfaces to generate propulsion. From an external perspective, this looks like chaos, but internally it is coordination without hierarchy, a network solving problems faster than a single command center ever could. In a reef filled with sharp edges, narrow gaps, and unpredictable currents, this flexibility translates directly into survival. The intelligence underpinning these abilities extends beyond immediate reactions into memory and learning. Octopuses are capable of recognizing specific locations, remembering successful hunting grounds, and returning to them repeatedly over time. They learn which holes tend to harbor prey, which routes offer safe passage, and which areas attract predators. This spatial memory allows them to operate like professionals rather than opportunists, revisiting productive zones with efficiency rather than rediscovering them through trial and error each time. Such behavior suggests an internal mapping system that tracks both reward and risk across a dynamic environment. This capacity for learning introduces a darker edge to octopus behavior because it enables pattern exploitation. An octopus that identifies predictable prey routines or seasonal abundance can time its activity to coincide with maximum payoff. It may adjust hunting schedules to avoid peak predator presence, forage under specific light conditions that favor camouflage effectiveness, or exploit human-altered environments where structures create artificial shelters. In this sense, the octopus does not merely adapt to its environment, but actively studies it, refining strategies over time with a level of persistence that borders on obsession. Escape behavior further illustrates this adaptability. When threatened, an octopus does not default to a single response, but selects from a repertoire that includes rapid jet propulsion, sudden camouflage shifts, ink release, and environmental manipulation. Ink clouds serve not only as visual obscurance, but as chemical decoys that confuse predators' senses, allowing the octopus to slip away while the attacker investigates a false target. Simultaneously, the octopus may alter its texture and color mid-flight, ensuring that even if pursued, it becomes harder to track against a changing background. These layered defenses operate in concert rather than isolation, compounding their effectiveness. The cost of this intelligence is a life lived intensely rather than long. Octopuses grow quickly, reproduce once, and die young by vertebrate standards, compressing learning, mastery, and execution into a brief window. This life history strategy favors rapid acquisition of skills and aggressive exploitation of opportunities because there is no time for redundancy or prolonged experimentation. Every successful hunt and every narrow escape feeds directly into reproductive success, ensuring that the genetic and behavioral foundations of intelligence persist despite individual brevity. Ecologically, octopuses exert pressure disproportionate to their numbers. By targeting a wide range of prey and exploiting shelter-rich habitats, they influence population dynamics at multiple levels. Their predation shapes the behavior of crabs, fish, and mollusks, forcing prey to adjust movement patterns, shelter use, and timing. In turn, these changes ripple outward, affecting algae growth, coral health, and nutrient cycling. The octopus does not dominate ecosystems through sheer consumption, but through disruption, injecting unpredictability into systems that would otherwise settle into equilibrium. What distinguishes the octopus from other intelligent predators in this narrative is its solitude. There is no pack, no pod, no colony reinforcing strategies through shared learning in the open. Instead, each octopus builds its own internal archive of solutions, refining tactics independently while relying on genetic predispositions that favor curiosity and flexibility. This makes their intelligence harder to observe and quantify because it does not manifest as obvious cooperation or repeated spectacle, but as quiet efficiency and adaptive subtlety. This solitude does not diminish their impact because intelligence does not require witnesses to be effective. An octopus slipping unseen through a reef, altering its environment with small, precise actions, can reshape local dynamics as thoroughly as a coordinated group of larger predators. Its unfair advantage lies not in strength or numbers, but in the ability to collapse the distinction between self and surroundings, turning the reef into an extension of its own body and mind. Seen in this light, the octopus fits seamlessly into the broader theme of strategic survival, demonstrating that dominance in nature can emerge from invisibility as much as force. Where others rely on alliances, speed, or sheer mass, the octopus rewrites the rules by becoming unreadable, unpredictable, and relentlessly adaptive. It does not need allies because it carries an ecosystem's worth of solutions within its skin and arms, deploying them with precision whenever conditions demand. The reef remains crowded and dangerous. Yet for the octopus, it is never fixed, never finished, and never fully hostile. It is a canvas of opportunity, reshaped continuously through perception and action. In that sense, the octopus represents the purest expression of unfair advantage in the wild, a solo strategist whose intelligence turns complexity itself into the ultimate weapon. Light behaves strangely beneath the surface, bending, scattering, and dissolving into gradients that shift with every ripple of water. In this unstable visual environment, survival depends not only on what an animal can see, but on how it can be seen, or more importantly, how it can control what others believe they are seeing. Among the coral shelves and sandy flats where visibility can change in seconds, cuttlefish operate with a level of visual authority that feels almost unfair. Not because they are hidden, but because they actively rewrite the visual rules of the battlefield. They are not merely camouflaged animals reacting to their surroundings, but visual engineers projecting information, misdirection, and threat through a living display system embedded directly in their skin. At the core of this system lies one of the most sophisticated biological interfaces on Earth, a layered network of chromatophores, iridophores, and leucophores working in concert under direct neural control. Chromatophores act as expandable pigment sacs, each one surrounded by tiny muscles that contract or relax in response to electrical signals from the nervous system. When expanded, they reveal dark pigments such as browns, reds, and blacks. When contracted, they disappear, allowing lighter layers beneath to dominate. This mechanism alone allows rapid shifts in pattern and contrast, but it is only the surface layer of a deeper optical toolkit. Beneath the chromatophores sit iridophores, structures that reflect specific wavelengths of light, producing shimmering blues, greens, and metallic sheens that change with viewing angle rather than pigment concentration. Below them, leucophores scatter ambient light broadly, acting as a brightness control that helps the cuttlefish match overall luminance rather than specific color. What makes this system extraordinary is not just its complexity, but its speed and precision. Unlike reptiles or fish that rely on hormonal changes to adjust coloration over seconds or minutes, Cuttlefish operate on a neural timescale. Signals travel directly from the brain to the skin, allowing patterns to shift in fractions of a second, fast enough to respond to sudden threats or fleeting opportunities. This immediacy transforms the skin into a real-time display, capable of broadcasting information, suppressing it, or reshaping it moment by moment. Camouflage, intimidation, courtship, and deception are not separate modes, but interchangeable visual languages drawn from the same interface. When a cuttlefish rests on the seafloor, it does not simply fade into the background, because perfect invisibility is rarely the goal. Instead, it samples the environment visually, adjusting contrast, texture, and brightness until its body dissolves into statistical noise. Edges blur, shadows align, and even the illusion of depth is manipulated through subtle patterning that mimics the grain of sand or the fractured geometry of coral rubble. Raised papillae add texture, breaking up the outline further, while subtle motion remains suppressed to avoid triggering attention. The result is not a static disguise, but a continuously updated visual approximation that tracks changes in light and perspective as currents move overhead. Yet this same skin can flip instantly from invisibility to dominance. When threatened or challenged, cuttlefish often deploy high-contrast patterns, bold striping, or sudden flashes of iridescence that exaggerate size and intent. These displays are not random bursts of color, but structured signals evolved to exploit visual processing biases in predators and rivals. Rapid contrast changes overwhelm attention systems, forcing observers to reassess threat level in a critical moment where hesitation favors the cuttlefish. Even larger animals may pause, not because the cuttlefish is physically dangerous, but because its display injects uncertainty into the encounter. This uncertainty becomes a weapon during hunting, where cuttlefish operate not as chasers, but as precision predators. They stalk slowly, often freezing mid-motion for extended periods, aligning their bodies with background features to eliminate movement cues. Preyfish, accustomed to detecting predators through motion and contrast, fail to register the cuttlefish as a threat, because it presents neither. When the moment is right, the cuttlefish strikes with speed that feels unreal, launching two specialized feeding tentacles forward in a ballistic motion that unfolds faster than the eye can track. These tentacles, stored compactly beneath the head, extend explosively to seize prey with adhesive clubs before retracting just as quickly. This strike is not simply fast, it is surgically precise. The cuttlefish calculates distance, angle, and timing before committing, because failed strikes waste energy and reveal position. Visual depth perception, enhanced by the spacing of the eyes and advanced neural processing, allows accurate range estimation even in distorted underwater optics. Once the prey is captured, the cuttlefish subdues it efficiently, using a sharp beak capable of piercing scales and bone. The entire sequence unfolds in less than a second, a compressed burst of action following minutes of stillness. What elevates this hunting strategy beyond raw speed is the integration of display into deception. Cuttlefish have been observed using dynamic patterns not just to hide, but to distract, projecting false motion or drawing attention away from the true axis of attack. A ripple of contrast across the body can pull a prey's focus toward one side, creating a half-second opening that aligns perfectly with the tentacle launch. In competitive encounters, similar displays can misdirect rivals, obscuring intent or masking approach. These visual feints operate like sleight of hand, exploiting the limitations of attention rather than overwhelming them. The effectiveness of these tactics depends on the architecture of the cuttlefish nervous system, which dedicates enormous processing power to visual interpretation and motor control. A large proportion of the brain is devoted to analyzing visual input and translating it into coordinated skin responses. Unlike animals that rely on pre-programmed patterns, cuttlefish generate displays contextually, adjusting pattern density, orientation, and contrast based on the specific environment and audience. This flexibility suggests a level of perception-action coupling that allows rapid experimentation and refinement, essential in habitats where conditions change constantly. From an evolutionary perspective, this system represents a shift away from brute force toward informational dominance. Cuttlefish do not need to outrun predators or overpower prey because they manipulate perception itself. By controlling how they appear, they control how others behave, shaping interactions before physical contact occurs. This strategy reduces injury risk and energy expenditure, advantages that accumulate over time and translate into higher survival and reproductive success. The ecological implications extend beyond individual encounters. Cuttlefish predation influences the behavior of small fish and invertebrates, forcing them to rely on group vigilance and rapid response rather than camouflage alone. This pressure selects for prey that can detect subtle anomalies in visual fields, driving an arms race of perception and deception. In turn, predators that rely heavily on sight must contend with an opponent that can rewrite the visual environment, reducing the reliability of their sensory input. The result is a dynamic system where information becomes as important as force. Cuttlefish also use their display system in social contexts, particularly during competition and reproduction, where visual signaling determines access to mates and territory. Males may present different patterns on each side of their body simultaneously, directing courtship signals toward females while displaying threat patterns toward rival males. This split signaling demonstrates an ability to manage multiple visual conversations at once, further reinforcing the idea that the skin functions as an interface rather than a static trait. Such complexity challenges assumptions about invertebrate simplicity, revealing cognitive capacities shaped by ecological necessity rather than phylogenetic proximity to humans. Despite their visual brilliance, cuttlefish remain vulnerable because intelligence does not eliminate risk, it redistributes it. Predators that rely less on vision and more on chemical or acoustic cues can bypass visual deception, forcing cuttlefish to layer defenses rather than depend on a single solution. Ink release, rapid jet propulsion, and abrupt pattern shifts serve as contingency plans, activated when visual control alone fails. This redundancy reflects a broader principle in survival engineering, where no single adaptation is sufficient, but combinations create resilience. The immediacy of cuttlefish skin control underscores a fundamental difference between aesthetic beauty and functional design. To human eyes, their patterns appear artistic, even mesmerizing, yet every flicker and shimmer serves a purpose grounded in survival. There is no decoration without function, no display without intent. Beauty emerges as a byproduct of efficiency, not a goal in itself. This reframing strips away sentimental interpretations and replaces them with a more accurate appreciation of what the animal is actually doing. Seen through this lens, cuttlefish are not performers, but operators running a complex interface under pressure. Their skin is a dashboard displaying threat levels, movement vectors, and strategic options in real time. Camouflage is not concealment, intimidation is not bravado, and iridescence is not ornamentation, because all are components of a unified control system optimized for rapid decision-making in hostile conditions. The battlefield is visual, and the cuttlefish owns the screen. This mastery of perception aligns perfectly with the broader theme of unfair advantage, because it allows cuttlefish to dictate terms without direct confrontation. They decide when to be seen, how to be interpreted, and what information to reveal or suppress. In a world where milliseconds matter, this control over perception translates directly into survival. Allies are unnecessary when the environment itself can be rewritten to serve your needs. In the end, the cuttlefish exemplifies a form of intelligence that operates beneath awareness, shaping outcomes before opponents realize a contest has begun. Its displays are not expressions, but commands issued to the sensory systems of others. By the time a predator or prey reacts, the decisive moment has already passed. This is not beauty for admiration, but interface for warfare, a reminder that in nature, the most powerful weapons are often the ones that never look like weapons at all. The reef floor is crowded with bodies that look fragile until pressure is applied and then refuse to yield. Shells, carapaces, calcified plates, and layered armor dominate this world, because survival in shallow tropical seas favors anything that can absorb impact, deflect bites, or turn jaws into useless levers. For most predators, this creates a constant negotiation between effort and reward, where thick armor means wasted energy, broken teeth, or abandoned prey. Yet threaded through this landscape of defensive excess is an animal so small it is often overlooked, yet so violently specialized that it short-circuits the rules entirely. The mantis shrimp does not negotiate with armor because it breaks it, turning the physics of water itself into a weapon that ignores scale and shatters expectations. At first glance, a mantis shrimp appears unremarkable, its body tucked low against the substrate, eyes perched on mobile stalks that rotate independently as it scans its surroundings. It moves cautiously, retreating quickly into a burrow carved into coral rubble or sand, a narrow tunnel that functions as both shelter and ambush point. This restraint is deceptive because beneath that measured posture lies one of the most extreme strike mechanisms ever evolved. The mantis shrimp's raptorial appendages are not claws in the traditional sense, but highly modified limbs designed to accelerate with astonishing speed, folding under tension like loaded springs until the moment of release. When that moment arrives, the strike unfolds faster than the nervous systems of most animals can register. The appendage snaps forward in a fraction of a millisecond, reaching peak acceleration so intense that it briefly boils the surrounding water, creating cavitation bubbles that collapse with explosive force. This secondary shockwave amplifies the impact, meaning the mantis shrimp delivers not just a physical blow, but a compound event where force and pressure converge almost simultaneously. For prey, this means that even if the initial strike misses by a narrow margin, the collapsing cavitation bubble can still stun, injure, or kill through sheer pressure change. The implications of this are profound, because water is usually a medium that cushions blows rather than transmits them. Most underwater strikes are dampened by drag, limiting speed and force. The mantis shrimp bypasses this constraint by operating in a regime where inertia and elasticity dominate, allowing it to briefly outrun the physics that govern larger bodies. Its strike is not powerful because it is strong, but because it is optimized to exploit material limits, pushing biological tissue to the edge of what is mechanically possible. This makes the mantis shrimp less a brute force predator and more a living physics experiment that happens to feed on snails. On reefs, this capability matters because armor is everywhere. Snails thicken their shells, crabs reinforce their carapaces, and bivalves clamp shut with muscular force that resists prying. For many predators, these defenses represent a cost-benefit barrier because breaking them takes time and exposes the attacker to risk. The mantis shrimp treats these defenses as irrelevant, smashing through shells that would resist repeated blows from larger animals. A single well-placed strike can fracture calcium carbonate structures instantly, granting access to nutrient-rich prey with minimal delay. This efficiency has evolutionary consequences because it removes the selective advantage of armor against this particular predator. In areas where mantis shrimp are common, prey species face a dilemma, as thicker shells may protect against fish and crustaceans, but offer no safety from a punch that ignores thickness entirely. This creates localized evolutionary pressure that favors behavioral avoidance over physical defense, forcing prey to alter habitat use, activity timing, or burrow depth, rather than investing endlessly in armor that no longer guarantees survival. Behaviorally, mantis shrimp are not passive hunters waiting for opportunity, but territorial operators that defend specific patches of reef as personal property. Their burrows serve as command centers, offering protection while anchoring their presence in the environment. From these positions, mantis shrimp monitor movement patterns, respond to intrusions, and launch strikes with precision born of familiarity with local terrain. This territoriality is not incidental, but strategic, because knowing the layout of a hunting ground increases strike success and reduces exposure to predators. Threat displays reinforce this ownership. When confronted by rivals, mantis shrimp do not immediately strike, but often engage in ritualized posturing that showcases their weaponry. Raptorial appendages are raised and flexed, bodies stiffen, and eyes lock onto the opponent, signaling both readiness and confidence. These displays serve to resolve conflicts without unnecessary damage, because while mantis shrimp can deliver devastating blows, repeated combat carries risk even for the best-armed individual. By advertising capability, they reduce the likelihood of escalation, conserving energy for feeding rather than fighting. When combat does occur, it is decisive. Strikes are aimed at vulnerable points, and encounters often end quickly, with one individual retreating rather than absorbing repeated blows. This calculated aggression reflects a balance between dominance and survival, because owning territory is only useful if the owner remains alive and functional. The mantis shrimp's behavior illustrates that intelligence in the wild often manifests as restraint, guided by confidence, rather than indiscriminate violence. Sensory adaptations further support this precision-based lifestyle. Mantis shrimp possess some of the most complex eyes in the animal kingdom, capable of detecting polarized light and a wide range of wavelengths. While their visual processing differs from that of vertebrates, it provides acute motion detection and environmental awareness, allowing mantis shrimp to judge distance, orientation, and timing with extraordinary accuracy. This sensory input feeds directly into motor execution, ensuring that strikes occur at optimal angles and ranges rather than through trial and error. The ecological role of mantis shrimp extends beyond their immediate predation, because their burrowing activity alters substrate structure, influencing sediment turnover and microhabitat availability. Burrows provide shelter not only for the mantis shrimp itself, but for smaller organisms that exploit abandoned tunnels or peripheral cavities. In this way, mantis shrimp function as ecosystem engineers on a small scale, reshaping the reef floor through repeated excavation and occupation. Their presence also influences the behavior of larger predators, which learn to treat mantis shrimp with caution despite their size. Fish that would readily consume other crustaceans hesitate when confronted with an animal capable of delivering injurious strikes. This deterrence effect alters feeding patterns, granting mantis shrimp a measure of protection disproportionate to their physical dimensions. Size becomes less relevant when capability is extreme, reinforcing the idea that evolutionary success is not strictly correlated with mass or visibility. From a physiological perspective, maintaining such a weapon system demands specialized materials and repair mechanisms. The striking appendages are reinforced with mineralized structures that resist fracturing despite repeated high-energy impacts. Microstructural organization dissipates stress, preventing catastrophic failure that would otherwise render the animal helpless. This durability allows mantis shrimp to strike repeatedly over a lifetime, sustaining performance through constant use rather than relying on expendable adaptations. Energy economics further underscore the advantage of this design. By resolving encounters quickly and efficiently, mantis shrimp minimize time spent exposed outside burrows, reducing predation risk while maximizing intake. Each successful strike yields immediate reward without prolonged struggle, aligning perfectly with the reef's competitive environment, where hesitation can attract unwanted attention. This efficiency allows mantis shrimp to thrive in densely populated habitats without requiring alliances or cooperative strategies. The absence of partnership is central to understanding how mantis shrimp fit within broader ecological narratives of cooperation and coordination. While many reef predators rely on teamwork to overcome defenses or herd prey, the mantis shrimp internalizes the solution, embedding the necessary force and precision within its own anatomy. It does not recruit allies or manipulate space collectively, because its weapon system renders such strategies unnecessary. In evolutionary terms, this represents a different path to dominance, one where specialization replaces cooperation rather than complementing it. This independence carries risks, because failure cannot be shared or mitigated through group behavior. A broken appendage or misjudged strike has immediate consequences, leaving the individual vulnerable until recovery occurs. Yet the persistence of mantis shrimp across reef systems suggests that the balance favors specialization, because the payoff of overwhelming force outweighs the cost of isolation. Their success demonstrates that ecological niches can be filled by radically different strategies, each valid within specific constraints. The wonder of mantis shrimp lies not only in their physical capability, but in what they reveal about the diversity of solutions evolution can produce. In a world where many animals adapt by becoming faster, larger, or more social, the mantis shrimp adapts by becoming precise beyond reason, compressing power into a form so small it defies intuition. It reminds us that the reef is not dominated solely by visible giants or coordinated hunters, but by innumerable small specialists whose impact is felt through sudden absence rather than constant presence. Seen up close, the mantis shrimp is not a novelty or curiosity, but a distillation of evolutionary logic pushed to an extreme. Every aspect of its biology converges on a single outcome, which is to deliver decisive force exactly when needed and nowhere else. This focus strips away excess, leaving an organism that operates like a tool sharpened beyond comfort, efficient, ruthless, and perfectly adapted to its role. In the context of the reef's ongoing arms race, the mantis shrimp occupies a unique position as a reminder that scale is negotiable and fairness is optional. It does not need partners, elaborate strategies, or overwhelming numbers, because its advantage is embedded at the molecular and mechanical level. The reef may appear tranquil from above, but beneath that calm lie countless confrontations shaped by physics as much as biology. Among them, the mantis shrimp stands as proof that even in a world of giants and alliances, the smallest monsters can hit hardest. The ocean is full of specialists, predators engineered for specific tasks, tuned to particular prey, habitats, and routines that repeat with reassuring predictability. Reef hunters memorize coral corridors, deep divers commit to darkness, and pack predators rely on coordination to tilt probability in their favor. Against this backdrop of optimization and planning moves a very different force, one that refuses to be pinned to a single strategy or place. The tiger shark drifts through marine systems like a variable introduced into an otherwise stable equation, breaking assumptions simply by existing. It does not need to be the fastest, the cleverest, or the most coordinated, because its advantage lies in uncertainty, a roaming presence that turns transition zones into pressure points and punishes hesitation wherever it appears. Unlike specialists that structure their lives around narrow diets or fixed territories, tiger sharks operate on breadth. Their range spans vast distances, crossing open ocean, skirting reefs, cruising along continental shelves, and slipping through island channels with equal ease. This mobility is not random wandering, but a deliberate exploitation of edges, the ecological seams where different habitats collide and animals are forced to adjust behavior. At these boundaries, prey species are most vulnerable because movement between safe zones requires exposure and familiarity breaks down. Tiger sharks patrol these liminal spaces not as ambush predators waiting in one place, but as roaming auditors, checking the margins for mistakes. Their diet reflects this philosophy. Tiger sharks consume fish, turtles, seabirds, marine mammals, carrion, and an astonishing array of inedible objects that reveal a willingness to test anything encountered. This opportunism is often misunderstood as indiscriminate feeding, yet from an ecological perspective, it represents resilience. By refusing to specialize, tiger sharks insulate themselves from fluctuations in any single prey population, allowing them to persist where others decline. This dietary flexibility also means that no species moving through their range can safely assume it is irrelevant, because the shark's menu is defined by opportunity rather than preference. The effectiveness of this strategy becomes clear in how tiger sharks hunt. They do not commit to prolonged chases that drain energy and reveal intent, nor do they rely on complex coordination that demands perfect timing. Instead, they move steadily, conserving energy, scanning continuously, and accelerating only when conditions align. This creates a psychological presence as much as a physical one, because prey animals rarely see a tiger shark coming from afar. The shark appears at moments of transition when attention is divided, energy is already expended, and escape routes are poorly defined. The strike, when it comes, feels sudden, not because the shark is fast, but because it has waited until speed is unnecessary. Edges amplify this effect. Reef drop-offs, where shallow coral shelves collapse into blue void, concentrate movement as fish and turtles navigate between feeding grounds and deeper refuge. Channels between islands funnel currents and animals alike, compressing space and reducing options. Murky coastal waters obscure vision, forcing reliance on senses that the tiger shark has mastered. By patrolling these zones, the shark positions itself where probability favors it, allowing encounters to resolve quickly rather than through extended pursuit. Sensory adaptations underpin this confidence. Tiger sharks possess an acute sense of smell, capable of detecting minute chemical cues dispersed through water, allowing them to track injured or stressed animals long before visual contact occurs. Their lateral line system detects low-frequency vibrations produced by struggling prey, swimming fish, or even subtle pressure changes caused by movement against currents. These signals cut through murk and darkness, providing a constant stream of information that guides the shark toward opportunity. Vision, while important, becomes secondary in these contexts, because the tiger shark does not need clarity to commit, only confirmation. This sensory integration gives tiger sharks an unusual comfort in environments that deter other predators. Murky water, where visibility collapses and obstacles multiply, does not reduce their effectiveness because their strategy does not depend on precise visual targeting at long range. Instead, they rely on proximity and timing, closing distance quietly until the final moment. Prey animals accustomed to spotting danger from afar find themselves operating blind, forced to guess rather than react. In these conditions, confidence becomes a weapon, because hesitation favors the animal willing to commit under uncertainty. That confidence is evident in the tiger shark's body language, which lacks the frantic adjustments seen in pursuit specialists. Their swimming is steady, deliberate, and unhurried, conserving energy while projecting inevitability. This demeanor influences prey behavior, as animals detect pressure not through direct sight, but through subtle environmental cues, altered currents, and chemical traces that signal danger without revealing its source. The shark does not need to chase every target, because its presence alone can redirect movement, pushing prey into tighter spaces or less favorable angles where mistakes multiply. Importantly, tiger sharks do not dominate ecosystems through sheer consumption, but through influence. Their roaming patterns shape the behavior of other predators, prey, and even entire food webs. Species that might forage freely in the absence of such a threat adjust timing, habitat use, and group structure when tiger sharks are common. This creates a landscape of fear that redistributes activity across space and time, preventing overexploitation of any single area. In this way, tiger sharks function as regulators, enforcing balance not by constant predation, but by maintaining unpredictability. This role becomes especially significant in systems where other apex predators are absent or reduced. Without roaming generalists to patrol boundaries, prey species may concentrate in predictable zones, intensifying grazing or foraging pressure and destabilizing habitats. Tiger sharks counter this tendency by refusing to respect those concentrations, moving fluidly between systems and preventing any single strategy from becoming dominant. Their impact is diffuse rather than localized, spread across vast areas through repeated, low-intensity interactions that accumulate into systemic change. The lack of reliance on alliances further distinguishes tiger sharks from many high-profile predators. They do not hunt in packs, coordinate roles, or share kills, because their strategy does not require reinforcement. Cooperation introduces complexity and dependency, while solitude preserves flexibility. A lone tiger shark can exploit opportunity anywhere within its range, adjusting instantly to changing conditions without waiting for partners. This independence allows them to operate continuously, unaffected by social dynamics that might constrain other predators. Yet solitude does not mean simplicity. Individual tiger sharks exhibit learning and memory, recognizing productive routes, seasonal patterns, and recurring opportunities. They remember where prey transitions occur, when certain species move, and how environmental conditions influence success. This knowledge accumulates over time, refining movement patterns into efficient circuits rather than random wandering. The shark becomes a mobile archive of ecological information, carrying experience across habitats and linking distant systems through repeated visitation. From the prey's perspective, this makes tiger sharks particularly unsettling because they cannot be avoided through specialization alone. A turtle may evolve armor, a fish may school tightly, a seal may rely on speed or group vigilance, yet none of these adaptations guarantee safety from a predator that exploits moments rather than methods. The tiger shark's unpredictability erodes the effectiveness of single-solution defenses, forcing prey to diversify strategies and remain vigilant across contexts rather than relying on a single refuge. This dynamic illustrates a broader principle in evolutionary ecology, which is that generalists often shape systems as profoundly as specialists, not by excelling at one thing, but by preventing others from settling into stable patterns. Tiger sharks embody this principle at scale, acting as mobile stressors that test assumptions wherever they roam. Their presence ensures that no habitat edge becomes complacent, no transition unguarded, and no movement routine entirely safe. For humans, the mystique surrounding tiger sharks often centers on their reputation for unpredictability, a label that obscures the logic underlying their behavior. They are not chaotic, but context-driven, responding to cues and probabilities rather than fixed scripts. Understanding this reframes encounters not as random acts of aggression, but as outcomes of being in the wrong place at the wrong moment within a system governed by transition and pressure. The shark did not seek a particular target, but exploited an opening created by movement, distraction, or environmental constraint. This reframing also highlights why tiger sharks are difficult to replace ecologically. Removing them does not simply reduce predation, but alters the geometry of risk across entire regions. Without roaming enforcers to patrol edges, systems drift toward predictability, allowing certain species to dominate and others to retreat. Over time, this can simplify habitats, reduce resilience, and amplify the impact of disturbances. Tiger sharks counteract this drift through presence rather than intervention, maintaining tension that sustains diversity. As the shark fades into blue once more, leaving behind only altered currents and unsettled prey, its influence persists invisibly. Routes change, behaviors adjust, and energy redistributes across the ecosystem in response to a predator that did not linger or announce itself. This is the essence of the tiger shark's role, not as a tyrant enforcing order through constant force, but as a roaming wildcard that ensures no plan remains unchallenged for long. In the broader narrative of ocean strategy, tiger sharks occupy a unique position. They are neither architects of cooperation nor masters of specialization, but enforcers of uncertainty, whose value lies in disrupting certainty itself. No alliance is required when presence alone reshapes behavior, and no elaborate tactic is necessary when patience and breadth do the work. The ocean remains vast and dangerous, but with tiger sharks moving through its seams, it never becomes predictable, and in that unpredictability, balance is preserved. In the crowded architecture of the coral reef, size is usually a liability. Small bodies are fast, but they are also fragile, easily crushed, swallowed, or torn apart by predators that treat the reef like a buffet line. Armor helps, speed helps, numbers help. Yet for the smallest fish, these defenses are often insufficient against hunters that combine patience, precision, and overwhelming force. In this environment, survival does not always belong to the strongest or the smartest in isolation, but to those that embed themselves into something more dangerous than any predator wants to challenge. Clownfish do exactly that, building their lives inside one of the reef's most lethal organisms and turning borrowed danger into permanent protection. A sea anemone is not a shelter in the conventional sense. Its tentacles are lined with thousands of stinging cells called nematocysts, microscopic harpoons loaded with toxins designed to paralyze prey or deter attackers on contact. For most fish, brushing against an anemone is a catastrophic mistake, resulting in immediate pain, disorientation, or death. The anemone does not discriminate, and it does not forgive, because its survival depends on turning contact into capture. It is a stationary predator in a mobile world, compensating for its immobility with chemical violence so effective that few animals dare to approach. Yet nestled among these tentacles, clownfish move freely, weaving through lethal threads with casual familiarity. They do not flinch, recoil, or show signs of distress, because the anemone's weapons simply do not fire against them. To an outside observer, this looks like immunity, but the reality is more nuanced and more fragile. Clownfish are not born protected, and they cannot simply dive into an anemone without consequence. Their survival depends on a delicate process of acclimation, a gradual introduction that allows their bodies to adapt chemically to an environment designed to kill them. This acclimation involves a specialized mucus layer coating the clownfish's skin, one that interferes with the anemone's ability to recognize the fish as prey. While the exact mechanisms remain an active area of research, it is clear that this mucus lacks certain chemical triggers that normally activate nematocysts, effectively rendering the clownfish invisible to the stinging system. The process takes time because an abrupt entry can still provoke stings, meaning young or newly displaced clownfish must approach cautiously, touching tentacles briefly and retreating repeatedly until tolerance is established. This vulnerability window is one of the most dangerous periods in a clownfish's life, because failure means death, and success means access to one of the safest refuges on the reef. Once acclimated, the anemone becomes more than shelter. It becomes infrastructure. The clownfish gains constant protection from predators unwilling to endure repeated stings, while the anemone gains something it cannot achieve alone: active defense and maintenance. Clownfish do not merely hide among the tentacles, they patrol them. Intruding fish that might nibble on the anemone, steal food, or harass its tissue are chased aggressively, despite the clownfish's small size. This behavior seems reckless until you understand the leverage involved, because a predator pursuing a clownfish risks contact with the anemone itself, turning a chase into self-inflicted injury. This is where the protection racket truly emerges. The clownfish uses the anemone as both shield and threat, daring others to approach while knowing the cost of escalation falls disproportionately on the intruder. Even larger fish often abandon pursuit once a clownfish retreats into the tentacles, because persistence offers no reward. The clownfish cannot outrun or overpower these predators, but it does not need to, because it has positioned itself inside a living weapon system that does the deterrence for it. The benefits flow both ways. Clownfish activity increases water circulation around the anemone, improving oxygen delivery and waste removal in a structure that otherwise depends on passive flow. Their movement may also deter parasites or sediment accumulation that could stress the anemone's tissues. Additionally, clownfish waste provides a localized source of nutrients, effectively fertilizing the anemone and its symbiotic algae, which rely on nitrogen to support photosynthesis. This steady input can enhance anemone growth and health, reinforcing the stability of the partnership. Food dynamics further entangle their lives. When clownfish dart out to feed, scraps and particles often fall back into the tentacles, providing the anemone with additional nutrition beyond what it captures directly. In some cases, clownfish actively deliver food items into the tentacles, an apparent investment in the anemone's well-being that pays off through continued protection. This mutual benefit transforms what could have been a one-sided refuge into a tightly coupled alliance where survival outcomes are linked. This relationship reshapes clownfish behavior in profound ways. Unlike many reef fish that roam widely in search of food, clownfish are intensely site-attached, rarely straying far from their host anemone. This reduces exposure to predators, but also limits foraging range, creating a trade-off between safety and opportunity. Clownfish compensate by exploiting local resources efficiently and defending their territory aggressively, ensuring that competitors do not siphon off the benefits of their protected zone. The anemone becomes both home and fortress, anchoring the clownfish's entire existence to a single point in space. Outside this fortress, the illusion of toughness evaporates. A clownfish swimming in open water is unremarkable, lacking speed, armor, or size to deter predators. Without the anemone, it becomes ordinary prey, subject to the same risks as countless other small reef fish. This dependency underscores how extreme the strategy is, because survival hinges on maintaining access to a specific partner. Lose the anemone, and the clownfish's defenses collapse almost instantly, exposing it to predation pressures it is poorly equipped to handle alone. This vulnerability has cascading implications for reef ecosystems. Anemones themselves are sensitive to environmental stress, including temperature changes, pollution, and physical disturbance. When anemones decline, clownfish populations follow, not because the fish lack adaptability, but because their entire survival strategy is built around a partner that cannot be easily replaced. This tight coupling makes clownfish effective indicators of reef health, as their presence reflects the stability of both the anemone population and the broader environmental conditions supporting it. The social structure of clownfish adds another layer of complexity to this protection system. Clownfish live in strict hierarchies within each anemone, typically consisting of a dominant breeding pair and several subordinate individuals. Size determines rank, and conflict is minimized through clear dominance relationships that reduce constant fighting in a confined space. This hierarchy ensures reproductive stability and prevents overcrowding, which could stress the anemone or attract predators through excessive activity. Social order, in this context, is not about cooperation for hunting or defense, but about maintaining equilibrium within a limited, high-value resource. Reproduction further ties clownfish to their anemone. Eggs are laid on nearby substrates, guarded by the male, while the proximity to the anemone provides a defensive buffer against egg predators. Hatchlings disperse into the plankton, facing extreme mortality before any return to reef life is possible, making successful recruitment rare and valuable. Those that survive must locate a suitable anemone and undergo the dangerous acclimation process again, repeating the cycle under intense selective pressure that favors precision over exploration. From an evolutionary perspective, this strategy represents a radical solution to the problem of being small in a dangerous world. Instead of evolving better escape responses or thicker scales, clownfish evolved compatibility, inserting themselves into an ecological niche guarded by chemistry rather than muscle. This solution is elegant but unforgiving because it demands exact alignment between physiology, behavior, and environment. Any disruption to one element threatens the entire system. Predators have adapted accordingly, learning that clownfish are rarely worth the effort unless they can be intercepted away from their anemone. This creates a spatial gradient of risk around the anemone, with danger increasing sharply just beyond the tentacles. Clownfish respond by minimizing excursions, timing forays carefully, and retreating at the first sign of threat. Their behavior reflects constant risk assessment, a reminder that protection is conditional and must be actively maintained through vigilance and restraint. Seen in this light, the clownfish is not a passive tenant, but an active enforcer. It does not simply benefit from the anemone's danger, it amplifies it by daring others to test it. The anemone's stings become more effective when paired with a mobile alarm system that identifies threats and provokes them into mistakes. This synergy transforms a stationary predator into a dynamic defensive network, one that extends its influence through the movements and decisions of a much smaller partner. This arrangement also reveals a broader truth about survival on the reef, which is that alliances need not be equal to be effective. The clownfish does not match the anemone in power, and the anemone does not match the clownfish in mobility, yet together they create a system more resilient than either could achieve alone. This mutual dependence blurs the line between individual and environment, illustrating how survival can emerge from integration rather than independence. To human observers, clownfish often appear charming, colorful, and harmless, their movements playful and their size disarming. Yet this perception misses the underlying reality of their existence. They live inside a loaded weapon, enforce territorial boundaries with calculated aggression, and depend on a chemical ceasefire negotiated at the cellular level. Their lives are not carefree, but finely balanced, contingent on maintaining a relationship that demands constant maintenance and precise behavior. In the end, the clownfish embodies a form of intelligence rooted not in problem-solving alone, but in strategic positioning. It does not fight predators directly or outrun them, but embeds itself within danger so thoroughly that threats are redirected elsewhere. The anemone is not merely a hiding place, but a deterrent, a resource, and a line that predators are unwilling to cross. Home, in this case, is not safety by absence of threat, but safety by overwhelming consequence. The anemone is home, and it is also a loaded gun, one that the clownfish knows exactly how to use. From a distance, a sea anemone appears almost decorative, a burst of color anchored to rock or coral, tentacles flowing gently with the rhythm of the water, as if the reef itself were breathing. This illusion is powerful because it aligns neatly with human instincts that associate softness, symmetry, and stillness with harmlessness. Yet the reef does not reward appearances, and the anemone's beauty is not an invitation, but a warning written in a language most animals understand instinctively. What looks like a flower is, in reality, a stationary predator whose entire existence revolves around turning contact into consequence, transforming a patch of reef into a chemically enforced exclusion zone. A sea anemone cannot chase prey, flee danger, or reposition itself when conditions shift. Its body is fixed in place, bound to substrate by a muscular base that grips rock with stubborn persistence. This immobility is not a weakness to be compensated for later, but the foundation around which every other adaptation is built. To survive without movement in a world of motion, anemones evolved one of the most effective contact-based weapons in the ocean, a microscopic arsenal embedded in every tentacle and ready to fire instantly. These weapons are the nematocysts, specialized stinging cells that operate like single-use harpoons under extreme pressure, waiting only for the slightest trigger to unleash their payload. Each nematocyst contains a tightly coiled barbed thread loaded with toxin, held under osmotic tension so intense that activation results in one of the fastest cellular events known in biology. When triggered by chemical or mechanical cues, the thread explodes outward, penetrating tissue and injecting venom in a fraction of a moment. This speed matters because it allows the anemone to bypass reaction time entirely. Prey does not feel pain and then flee. It is immobilized before awareness forms, muscles locked by neurotoxins that disrupt normal function. Even larger animals that brush against tentacles receive enough stings to cause immediate distress, reinforcing avoidance behavior after a single encounter. This system turns the anemone's immediate surroundings into a hazard zone, a ring of enforced distance that few animals are willing to violate repeatedly. Tentacles swaying in the current are not passive ornaments, but a dynamic perimeter, constantly sampling the water for contact, constantly armed. The movement that appears peaceful is in fact a form of reach, extending the anemone's lethal interface outward into the surrounding space. Anything that drifts too close is tested, and most fail that test instantly. As a predator, the anemone relies on this interface to capture food in an environment where opportunity arrives rather than being pursued. Small fish, crustaceans, and planktonic organisms carried by currents become meals when they collide with tentacles, paralyzed and transferred inward toward the central mouth. Digestion begins externally, enzymes breaking down tissue before ingestion completes the process. This method is slow compared to active hunting, but it is reliable, requiring little energy expenditure beyond maintenance and regeneration of stinging cells. As a defender, the anemone's role is even more consequential. Its tentacles deter not only prey-sized animals, but also many would-be predators large enough to consume the anemone itself. Repeated stings discourage grazing, and while some specialized animals can tolerate or avoid the venom, most fish learn quickly that proximity carries cost. Over time, this creates spatial patterns on the reef, where certain zones are left undisturbed simply because an anemone occupies them. These areas become pockets of enforced calm, not because they are safe, but because they are dangerous in a predictable way. It is within this chemically enforced perimeter that one of the reef's most famous partnerships emerges, transforming the anemone from a solitary hazard into the anchor of a living alliance. When a clownfish takes up residence among the tentacles, the anemone's role expands from predator to bodyguard, its stings forming the outer wall of a shared territory. Yet this relationship is not parasitic or one-sided, because the anemone gains tangible benefits from its tenant, benefits that alter how the reef interacts with both of them. The presence of a clownfish changes the dynamics around an anemone almost immediately. Fish that might otherwise nip at tentacles, steal captured prey, or harass the anemone are chased away aggressively, despite the clownfish's small size. This behavior works because the clownfish is not acting alone, but backed by the threat of stings that escalate any confrontation beyond what intruders are willing to endure. The anemone, in effect, gains mobility through the clownfish, extending its defensive reach outward and responding to threats before contact even occurs. Food dynamics shift as well. Particles dislodged during clownfish feeding drift back into the tentacles, increasing capture rates, while metabolic waste released by the fish enriches the surrounding water with nutrients that benefit the anemone and its symbiotic algae. Water movement generated by the clownfish improves circulation, enhancing oxygen delivery and waste removal in tissues that otherwise rely on ambient flow. These contributions are subtle but cumulative, improving the anemone's health and growth over time. The reef responds to this partnership as a single unit rather than two separate organisms. Predators learn to treat the anemone and clownfish as a combined threat, avoiding the area altogether rather than attempting precision strikes. Smaller fish alter foraging routes, steering clear of tentacle reach and the aggressive patrols that surround it. Over time, this creates a micro-territory with distinct behavioral rules, a zone where normal predator-prey dynamics are suppressed by the constant presence of chemical and behavioral deterrents. This suppression has ecological consequences that ripple outward. Anemone safe zones provide shelter for other small organisms that linger near the perimeter without crossing into danger, benefiting from reduced predator traffic. Algae and sessile invertebrates nearby experience different grazing pressures, as herbivorous fish avoid lingering too close. These changes reshape microhabitats, influencing species composition and energy flow on a scale small enough to be overlooked, yet large enough to matter when repeated across a reef. Importantly, the anemone's influence does not come from dominance or aggression in the traditional sense, but from reliability. Its stings are consistent, predictable, and unavoidable upon contact. This predictability allows other animals to incorporate the anemone into their mental maps of the reef, treating it as a fixed hazard much like a sharp drop-off or narrow crevice. Over time, these maps shape movement patterns, feeding strategies, and even reproductive site selection, embedding the anemone into the behavioral fabric of the ecosystem. Despite this power, the anemone remains vulnerable in ways that highlight the limits of chemical defense. Environmental stresses such as rising temperatures, pollution, and physical disturbance can damage tissues, reduce stinging cell effectiveness, or disrupt the symbiotic algae that supply much of the anemone's energy through photosynthesis. When stressed, anemones may retract tentacles, reduce feeding efficiency, or detach entirely, losing the very advantages that make them formidable. In such cases, the protective partnership collapses, leaving clownfish exposed and the reef's micro-territory dissolved. This fragility underscores a central truth about partnerships built on specialization. The anemone's poison is effective, but only under conditions that support its physiology. Remove those conditions, and the poison becomes insufficient to sustain the broader system that depends on it. The clownfish, for all its behavioral adaptations, cannot replace the chemical barrier the anemone provides, just as the anemone cannot replace the active defense and nutrient input of its tenant. Their success is interdependent, balanced on environmental stability that neither controls. From an evolutionary perspective, the anemone represents a path where immobility is not a handicap, but a defining constraint that drives extreme solutions. Instead of evolving speed or armor, it evolved inevitability, a guarantee that contact equals consequence. This strategy is costly, requiring constant regeneration of stinging cells and maintenance of delicate tissues, but it pays dividends by simplifying interactions. The anemone does not need to decide when to strike, because it always strikes, delegating decision-making to the nervous systems of others who learn to avoid it. The partnership with clownfish refines this strategy further, layering behavior atop chemistry to create a hybrid defense system. The anemone's poison provides the final line, while the clownfish acts as early warning and enforcement, reducing the number of times that line needs to be tested. Together, they form a deterrent more effective than either could achieve alone, not through shared intent, but through complementary capabilities. Seen through this lens, the gentle sway of anemone tentacles takes on a different meaning. It is not the calm motion of a passive organism, but the constant adjustment of an armed perimeter, a reminder that danger does not always announce itself through aggression or pursuit. Sometimes it waits, anchored, patient, confident that the world will come to it eventually. The reef is full of such waiting hazards, but few are as influential as the anemone, because few combine lethality with predictability so completely. Its presence reorganizes space, behavior, and relationships around it, shaping outcomes without movement or noise. In a system defined by motion, The anemone proves that stillness can be just as powerful, provided it is backed by consequence. In the end, the sea anemone stands as a reminder that some of the most effective partnerships in nature are forged not through cooperation alone, but through shared risk, mediated by chemistry. The anemone offers poison, the clownfish offers vigilance, and the reef responds by respecting the boundary they create. What appears to be a peaceful corner of color and motion is, in fact, a fortified position, one where survival is negotiated at the cellular level. Some alliances are built on speed, some on intelligence, and some, as the anemone makes clear, are literally built on poison. In the warm shallows of the tropics, danger does not always announce itself with size, speed, or noise. Sometimes it arrives as absence, as a failure of perception rather than an obvious threat. Sunlight pours through clear water, sand reflects pale gold, and visibility stretches uninterrupted toward the horizon, creating the illusion that nothing lethal could possibly hide here. This is the setting where people relax their guard, where animals lower vigilance, and where evolution has produced one of the most unfair weapons in the ocean. The box jellyfish does not hunt by pursuit, intimidation, or strategy in the familiar sense. It wins by existing almost invisibly in the exact places where confidence replaces caution, turning contact itself into catastrophe. At first glance, a box jellyfish barely registers as an organism at all. Its bell is near transparent, refracting light rather than blocking it, bending the surrounding water into subtle distortions that vanish unless viewed from the right angle. Unlike the flowing domes of many jellyfish, the bell has defined edges, a cube-like geometry that gives the animal its name while remaining difficult to detect in open water. There is no coloration to warn, no pattern to draw the eye, and no obvious movement to betray its presence beyond the gentle pulse that keeps it suspended. In a three-dimensional environment flooded with light, invisibility becomes a form of armor, because predators and prey alike depend on contrast to identify threats. Trailing from the corners of this bell are long, delicate tentacles, sometimes extending many body lengths into the surrounding water. These tentacles are not passive threads drifting harmlessly behind, but densely armed delivery systems packed with millions of microscopic stinging cells. Each cell houses a coiled harpoon capable of firing instantly upon contact, injecting venom through skin with astonishing efficiency. The length of the tentacles matters because it expands the box jellyfish's effective reach far beyond the visible body, creating an invisible perimeter that can intersect paths long before the animal itself is noticed. The venom delivered by these stings is among the most potent known in the marine world, designed not merely to subdue prey, but to overwhelm physiological systems rapidly. It targets the nervous system, the heart, and cellular membranes simultaneously, disrupting communication, causing intense pain, and triggering cascading failures that can lead to cardiac arrest in large animals. This is not venom optimized for prolonged struggle, but for immediate incapacitation, because the box jellyfish does not restrain prey mechanically. It relies on speed of effect, immobilizing fish almost instantly, so that tentacles can transfer them toward the bell for consumption. What makes this strategy especially terrifying is that it requires no pursuit. Box jellyfish do not chase prey through water or corner it against structures. Instead, they drift or maneuver slowly, positioning their tentacles like a suspended minefield. Fish swimming through these zones encounter venom before they register threat, often dying within moments. The jellyfish does not need to react, because the reaction is outsourced to chemistry that fires automatically upon contact. In this sense, the box jellyfish does not hunt actively, but waits for the environment to deliver victims into its weapon system. This waiting is not random. Box jellyfish possess a level of sensory awareness unusual among jellyfish, including clusters of simple eyes capable of detecting light, shadow, and obstacles. These eyes do not form detailed images, but they provide enough information to orient the animal relative to shorelines, mangrove roots, and structures where prey density is higher. Rather than drifting aimlessly, box jellyfish can navigate shallow coastal waters deliberately, avoiding obstacles while remaining in productive zones. This limited but effective perception allows them to exploit environments where invisibility provides maximum advantage. Clear tropical water amplifies this advantage dramatically. In such conditions, many predators rely on vision to detect threats and opportunities, scanning for movement or shape against a bright background. The box jellyfish defeats this system by offering neither, existing as a refractive anomaly rather than an object. Its tentacles, nearly invisible themselves, extend the danger zone into areas where fish feel safe to move quickly and confidently. The clearer the water, the less warning there is, because turbidity would at least reveal disturbance. In pristine conditions, the jellyfish becomes a perfect trap, its effectiveness increasing as visibility improves. This logic explains why shallow coastal environments, often perceived as safer than the deep ocean, can be far more dangerous. Depth brings darkness, pressure, and obvious predators, whose silhouettes and movements signal threat. Shallows bring light, warmth, and a sense of control that encourages exposure. Box jellyfish exploit this psychological gap, thriving in areas where vigilance drops and traffic increases. Beaches, estuaries, and calm bays become corridors of risk, not because of chaos, but because of predictability. Animals and humans alike move through these zones repeatedly, following routines that intersect with drifting tentacles again and again. Ecologically, the box jellyfish occupies a strange position. It is not an apex predator in the traditional sense, because it does not regulate populations through selective hunting or territorial dominance. Instead, it acts as a filter, removing individuals that pass through certain spaces at certain times. This creates pressure on prey species to adjust behavior, altering migration timing, swimming depth, and habitat use to minimize contact. Over time, these pressures shape local ecosystems, influencing where fish congregate and how energy flows through shallow systems. Unlike many predators, box jellyfish do not need to balance risk against reward. They are rarely targeted by other animals because their venom deters most would-be attackers immediately. Even dead or damaged individuals can deliver stings, reinforcing avoidance. This near-total lack of predation allows box jellyfish populations to persist with minimal checks beyond environmental conditions. When those conditions favor them, such as during certain seasons or temperature ranges, their presence can increase dramatically, transforming familiar waters into lethal zones almost overnight. Physiologically, the box jellyfish represents an extreme solution to survival without armor, speed, or size. Its tissues are fragile, easily damaged by physical contact or rough water. Yet this fragility is offset by a strategy that discourages contact altogether. The jellyfish does not survive by resisting force, but by making force unnecessary. Any organism that touches it pays a cost so high that repeat interactions are rare. This creates an ecological deterrent field, a space defined not by walls or teeth, but by consequence. For humans, encounters with box jellyfish illustrate the mismatch between perception and reality that defines their danger. There is no visual cue that reliably signals presence, no aggressive behavior to interpret, and no opportunity to react before venom is delivered. The pain associated with stings is often described as overwhelming, but pain is only part of the problem. Systemic effects can escalate rapidly, turning what seemed like a minor contact into a medical emergency within minutes. This is why box jellyfish are responsible for serious injuries and fatalities disproportionate to their size or visibility. Understanding this risk reframes how we think about marine danger. It is tempting to equate threat with size or ferocity, yet the box jellyfish demonstrates that efficiency and stealth can be far deadlier. Its success lies in exploiting assumptions, both biological and psychological, about where danger should reside. We expect predators to announce themselves through motion, form, or behavior, and the box jellyfish violates all three expectations simultaneously. There is no partnership here, no alliance or cooperative strategy. The box jellyfish stands alone, not because it is solitary by choice, but because its weapon system requires no reinforcement. It does not need speed, intelligence, or numbers when its environment and physiology do the work automatically. This is the ultimate unfair advantage, a system so optimized that interaction itself becomes lethal. As a closing chapter, The box jellyfish serves as a reminder that the ocean's most dangerous organisms are not always the ones that dominate headlines or inspire fear through spectacle. Sometimes they are the ones we fail to notice entirely. In clear water, invisibility is not a flaw, but a strategy, and drifting is not passivity, but precision. The box jellyfish does not chase, threaten, or warn. It waits, confident that movement, curiosity, and routine will deliver targets without effort. The reef and coastline may appear serene, but serenity is often a surface condition, masking layers of risk that operate quietly beneath. The box jellyfish embodies this truth perfectly, existing as a final lesson in unfair advantage. You do not fight it, outrun it, or outthink it. You avoid it, or you pay the price. In waters that look harmless, where light dances and danger seems absent, the box jellyfish reminds us that the most lethal rule of the ocean is simple and absolute: do not touch.